This is StarTalk. Neil deGrasse Tyson here, your personal astrophysicist, and we have our Cosmic Queries edition, a fan favorite. Chuck, you know it's a fan favorite.
They love it.
And we put out the expertise of our guest and what the topic is, and then we get flooded with questions. And today, we've got a colleague of mine, David Kipping, from up at Columbia University, the Department of Astronomy and Astrophysics. He has taproots from the UK at Cambridge University and University College London. And he's part of what they call the Cool Worlds Lab. David, welcome to StarTalk.
Thank you so much, everyone. Yeah, the name is not supposed to be like dope planets or something. That's right. Not what we're going for. Yeah. It really is cool, like actually temperature cool planets.
And you're no stranger to the social media platforms. You've got your own YouTube channel.
That's all pandemic to thank for that. I think, I've been making these videos for years and people just got into it recently.
So tell us, what's the Dope Ass Worlds Lab?
Cool Worlds Lab is, it's the research team I started here at Columbia. So, there was a team called the Cool Stars Lab in San Diego, I think. And I thought that was a great name because obviously it's a fun play on words and everyone's interested in cool stars. And as we've been discovering more and more planets, we know of lots and lots of planets which are close to their stars, but it's the planets which are far away from their star, where the temperatures are cool enough that we get really excited because then you have the possibility of liquid water or this kind of stuff. We're interested in moons. That's one of the big things we're interested in. That really doesn't directly have anything to do with temperature, but actually does kind of work out that way, that when you're far away from the star, there's a better chance of moon. So
yeah, but you're counting Earth as being far away from the sun in this vernacular.
In this picture. It's a cool world in this picture, I would say. Yeah.
Cool. All right, so why do we have so many exoplanets that are so close to their host star?
That's just detection bias, unfortunately. I mean, I wish it wasn't true.
All right, tell us about detection bias. Tell us about that. Because we hear about bias all the time, and usually it's some psychological bias. Right. No one is thinking that there could be actual scientific bias that has nothing to do with... Tell us what you mean by a detection bias.
Yeah, it's not bigoted astronomers in this case. That does sometimes happen, but that's not what's happening here. The real problem is that the most successful way of discovering planets is this transit method. Sure, you've talked about many times on StarTalk. The idea of as a planet eclipses in front of the star, it blocks out some of the starlight, and of course the star gets dimmer. But in order to get that chance alignment, it's much easier if the star and the planet are very, very close together. Right. When you put them far apart, to get that chance alignment, it's kind of hard to show, but it's kind of improbable that the longer the axis is, the less likely is you're going to get those two objects to line up. And so for that reason,
so this is like looking for your
car
keys under the lamppost, because that's where you're going to find them. So if you're going to look for planets, you're most likely to find just those planets that are close by. And they're so close that they're very hot for being so close to their host star. I guess that's the problem.
Unfortunately for me, I mean, some folks are fascinated by those hot planets. I'm obviously more interested in the cooler objects.
On the possibility of life, ultimately.
In part. I mean, as I said, a big part of one of the reasons I love these things is just exotica can happen out here. You can have icy rings. You can have exomoons. There's even a paper on the archive that will surely get debunked tomorrow claiming of a Trojan exoplanet at these kind of distances.
So first, tell everyone what the archive is. Tell us everyone about Trojan objects.
There's a regular posting, an electronic repository called the archive, but it's archive with an X. And astronomers can post discoveries, papers that they have. Usually they've been through peer review, but sometimes, like the paper that was up today, I don't think it had been peer reviewed yet. And there was a claim of 2 new planets which happen to be in the same orbit as each other.
Racetrack.
Yeah, they're chasing each other. So that's called a horseshoe orbit. And theoretically, that's possible. I just think a lot of us are pretty skeptical about the data for this particular case.
Okay. Gotcha. All right. And so then you said something about exomoons? What
we have rings, icy rings out here, moons, and liquid water, life. I mean, there's all sorts of fun jazz that can happen once you get far from the star.
That's why they're cool stars.
What's the largest planet that's ever discovered? How large could a planet get?
For planets, usually the biggest planet that was cold, if it was cool and there was no heat involved or anything like this, pretty much the biggest planet you can get is Jupiter sized. You actually, if you just spoon more mass onto Jupiter, it doesn't get any bigger. It just gets more massive and its density increases, but its physical size doesn't really change. In fact, if anything, actually gets slightly smaller. Get sliced slightly.
Okay, so often in the public, when people say big, they don't always know whether they're referring to size or mass. Right? I think those are conflated often when people are asking questions in the public. So you make a very interesting point. You can increase the mass of Jupiter by spooning matter into it, and the extra gravity actually compresses the gas more than it otherwise would.
Yeah. So in terms of the maximum mass, let's go that. Let's just keep spooning mass on. Eventually, it'll become a star. It kind of goes through this period of being a brown dwarf, but I think lots of us think, well, brown dwarfs, that's kind of a made-up category to some degree. It's effectively still just a type of Jupiter, some kind of super Jupiter. And eventually, when you start spooning enough mass on, you'll get to the critical point, which I think we can all agree something special happens, which is when hydrogen fusion occurs. There's enough pressure inside in the core of that object that hydrogen fusion occurs, and now you have a star. And that happens at about 80 Jupiter masses.
You've been spooning more and more mass onto it. So therefore, the pressures down in the middle keep going up.
Correct.
Okay.
So about 80 times the mass of Jupiter. So Jupiter is not close to being a failed star. People say Jupiter's a failed star. It has to be 80 times more, 80 times more mass to get. It's kind of a long way off, I would say, from being a failed star. But it has a similar size, physical size, to the smallest stars. That is true.
Jupiter already has more mass than all other planets combined.
Right.
But you're saying it could have been even more massive and we'd still call it a planet. And then nothing else matters in the solar system except the star and Jupiter. Like nothing. You know what I tell people, Chuck, that Jupiter is more bigger compared to Earth than Earth is compared to Pluto.
Okay.
So if you're an Earthling and you want to say, let's get rid of Pluto's planet status, and you feel good about yourself.
Right.
If we were Jupiterians, we could feel the same way and kick Earth out, and we'd have no recourse.
If you really want to get these planets big, you have to add heat. So you take one of these Jupiters and you park it next to a really hot star.
Oh, then it puffs up.
It puffs up. So then you can get up to something like 170% the size of Jupiter. So 1.7 times larger. Probably not quite. I don't think we have any ones that are twice as big, but they get pretty close to that limit.
So a tad under twice the size of Jupiter is kind of our limits for planets, no matter where they are.
As far as we know. I mean, that's the fun thing about science. You never know. Someone might make a discovery tomorrow of a three Jupiter-sized planet, and there's even ideas of dark matter planets. Dark matter planets would be extremely large, probably larger than the sun. In fact, it's a hypothetical, but dark matter doesn't like to clump. It's very diffuse. It interacts very weakly, and so it's kind of hard to collapse it down, to cool it down as normal gases. When normal gas gets hot, it cools down, it radiates, and so it cools down, the gas collapses, and eventually cools down to a point where you can actually start to form stars because the gas has concentrated so much. Right. Dark matter doesn't really do that, but there are some varieties of dark matter models that allow for a bit more clumpiness. It's allowed to kind of interact a bit more strongly. That could, it's a fairly extreme idea, but in some extreme versions, it could potentially form a dark matter planet, but it would be larger than the sun. It would, and of order of, just a few Earth masses, and it would be very weakly bound together. So it'd be a pretty.
But then, what right would you have to call it a planet?
That's for. I really don't care about.
It's a gathering of mass.
Yeah. People, you talked about Pluto. I never get into that debate. Call it whatever you want. It's interesting. It's an interesting world.
How many people are part of this lab?
Let's see. I have 3 graduate students right now, and at any one time, there's somewhere between sort of 3 and 6 undergraduates. It's sort of there's some stochastic variation in that sense.
All right. So this you just invented this out of whole cloth.
Yeah. I also have an editor as well for my videos, because there's a whole separate thing of the videos we make on YouTube. I work and he edits my videos, but isn't involved in the research directly.
And what's the name of your channel?
Just Cool Worlds.
Looking at Hanno Rain's Exoplanet app, There are more than 300 planets noted in the habitable zone of their stars, of which a vast majority of them are at least half the mass of Jupiter or bigger, sir. Is this just a result of how we're currently detecting planets, or do you think it's a potentially common occurrence for a gas giant to be in the habitable zone of its star?
Yeah, that's definitely something we're excited about. And it rings true. I mean, you have to be careful when you look at these catalogs, like on the app or on NASA Exoplanet Archive. It's another great website if you want to go through all of these yourself. I'm not sure if Hanno is still updating that app anymore. So I'm sure there's even more actually past that. But
because the total exoplanets are over 5,000. Seems to me we would have more than 300 in a Goldilocks zone. Yeah,
possibly.
Okay.
I'm not sure, but in any case, that you have to be careful because of all these biases, these detection biases, that you're only ever seeing a fraction of the true number. So people have done the calculation of correcting for that bias to actually figure out how many planets are there really in this temperate zone. And it turns out that you're right, that there are a surprisingly large number, about 50% of all sun-like stars, FGK type stars, we call them sun-like stars, they have planets with radii in between about twice that of the Earth, all the way up to the biggest Jupiter. So all of those are gas giants, mini gas giants, Neptunes, mini Neptunes, super Neptunes, Saturns, Jupiters.
So that's even correcting for the observer's bias.
Correct. Half of all stars have gaseous planets in their habitable zone, which obviously don't have solid surfaces.
Wait. That's something different from what you said. I thought half of all planets in the habitable zones are that size. You're saying half of all stars.
Correct.
Oh my God, that's a whole other.
That's a lot. That's a lot. Yeah,
that's
very common. That's from Kepler statistics. For Earths, we don't even know what the answer is.
Telescope designed specifically for these discoveries. Yeah.
Correct. Thank you. Yeah. Not the NASA mission that flew, 2009 to 2014, 15.
Sure.
So we know that there are lots and lots of those gaseous planets, which could have moons. And that's why we're so excited to look for them. And in fact, there may even be far more than Earth-sized planets at that distance. We actually don't know what the number is of how many Earths there are at that distance yet.
So so you like the moons because you like moons of gaseous planets because they give you a surface to hang out on.
Right. I mean, there could be more habitable moons than habitable planets in the universe. Other aliens could be looking at us thinking, what's going on over there? Why are they living on a planet?
I'm going to say that's the one cool thing that I like about Star Wars when it comes to how they envision other worlds and galaxies, solar systems, is that often they're going to a moon of a planet. They're not going to that planet. It's whatever system, but then where they're actually landing is a moon itself.
I would also add that the host planet is going to look way better in the sky from a moon than the moon is from the planet. Just thought I'd tell you that. Yeah. Just imagine Saturn in the night sky, just looming large.
Wow.
That would just be totally cool.
That is cool.
But,
yeah. I always wonder how history would be different had that happened to us. Like, how would we discover the laws of physics differently, celestial mechanics, the Kepler's laws of motions? Would the presence of such a large body in our sky accelerate it? Would it decelerate it? Obviously, there's all this kind of radio stuff flying off Jupiter as well. Would that affect the technology we develop on our home planet, our home world even? So it's ripe for science fiction. That's why Star Wars has so much fun with it.
So I think about it the opposite way, David. If we evolved on the surface of Venus, which is a very thick cloud cover, and it would just get light in the day and dark at night, but you wouldn't know how much delayed would astronomy have been? Because you'd have no idea what's going on outside of this fog.
Since some planets in our solar system have higher concentrations of certain elements, iron on Mars, for example, does that suggest our original solar nebula, once flattened by a centrifugal force, may have been ring-like with bands of certain elements that eventually formed the planets, sort of a solar system-sized version of Saturn's rings?
Oh, I like that.
Wow.
Because that would mean that different places within the ring would coalesce to form a planet and have a very different concentration from other places in the disk. So how does that all land with you, David?
That's a really interesting question. In terms of iron abundance, I'm not. I've not heard that before. That Mars has a higher iron abundance than the Earth.
I know
Especially,
Mercury wins. Mercury
definitely does. I know for
huge
sure
iron
Mercury
core,
does.
right?
But Mercury is somewhat of a strange case. Usually, the explanation we evoke for making sense of what's going on with Mercury is, I mean, generally we kind of assume that all the planets formed with roughly the same amount of iron, at least in a relative sense compared to their mass. But Mercury does seem to have a lot more iron than the other planets in a relative sense. And so our explanation for that is that it was basically struck by many, many meteorites with such high velocity, such high energy, they actually chipped away the outer layer of Mercury.
So you're saying it chips away pieces of Mercury that then just gets jettisoned into the solar system? Never to return?
Or even just vaporized to some degree from the impact and then leaked off as vapor. So that probably explains, we think, why Mercury has higher iron abundance. But generally, you assume that for the rest of the planets, it is uniform. And in fact, that is often treated as a default assumption when we look at other exoplanets. We assume that there's
you don't know for sure about Mars, though. We're not quite sure. You're not quite sure.
I'm not sure. I've never heard that before, so I'd have to fact check that. That Mars. I always like to be honest when I've not heard something before. I've never heard the fact that Mars has a higher iron abundance than the Earth. I'd be somewhat surprised if it's true, because I just from my expertise of looking at exoplanets, I know that many of my colleagues explicitly assume that the iron abundance is uniform throughout any given solar system, with exceptions like Mercury.
We can't deny Mars the fact that it's red because of iron in its outer crust. I mean, everywhere. That's pretty much just a rusty place.
I think that's partly due to the unique history of that planet and its distinct chemical environment and the oxidation that happened on its surface that is different from Earth and Venus.
You implied something that I want to tease out here because it's a very important scientific tool, really, that you can make an assumption about, you can make a reasonable assumption about how much iron you'd expect in all of the planets based on the iron that's in the sun, because the sun has most of the mass of the solar system. Then if the iron differs from that, you get to then look for an explanation for that. Correct. Which is a fascinating way to land on a new problem. We did that with the moon. The moon has hardly any iron. Yeah. So how do you become an object that big with no iron? So then we looked and we thought about it, and then we came with the collision hypothesis for the moon. So it's fun when something falls out of your expectations. You get novel accountings.
But that's actually why I don't like this strategy that many of my colleagues have of assuming explicitly that the iron abundance in the star is the same as the planets, because, as you just point out, there's already two counterexamples right there, and there's probably even more throughout the solar system.
I get that, but if it is different, then you get to look for why it's different, rather than say
we in exoplanets we have no way of directly measuring the iron abundance, at least not yet. I mean, I think the only way to do that would be if the planet was so hot, it was like Mustafar from Star Wars. It was like a lava world where the rock was literally gaseous, and then you could infer the composition of the rock from the atmosphere. But barring that, we have no way of measuring the chemical composition of what's inside.
How about Io around Jupiter? Aren't there active volcanoes there? Could you get some iron?
That's a good example. So yeah, kind of like a Mustafar-ish type system, right? Where you have extreme volcanism, where you can spew up the gases, and then you get a chance of sampling what was inside. Okay. Wow. You need that,
All right. You presumably have catalogs of exoplanets now. There's more than 5,000. So presumably they line up with each other in ways that reveal similarities. Is there an outlier among the 5,000 where nobody else looks like it?
I think it's hard to pick on one. There's several planets which come to mind in this case. One is one I helped kind of discover its weirdness of, immediately comes to mind because it got so much press attention when we released it. It was like 10 years ago now. And it was called TRACE 2b, and we called it Erebus, the darkest world. Erebus was the god of darkness, I think, in Greek mythology. So this planet is darker than coal. It's darker than black paint. It reflects less light than basically any material you can come across, except for Vantablack. Okay. But we don't know. It might be as dark as Vantablack. We only have an upper limit on its darkness. So
what is Vantablack?
Darker than Vantablack, as far as we can tell.
What is Vantablack?
It's the least reflective material that we know of to date. So it has an albedo of nothing. No.
Near zero, I guess.
Yeah, almost zero.
But wait. So, David, if it doesn't reflect any light, how do you know it's there?
From transits, it still casts a shadow. It still casts a shadow. When it passes in front of the star, it blocks out light. When it passes behind the star, we call that the occultation event. You get kind of a moment where you get to detect photons from the planet, light from the planet. So I can take a picture just here, just before the planet passes behind. And now I'm getting light from the planet and light from the star. And I take a photo of the two. And then I take a photo when it's behind. And now I've just got light from the star by itself. So subtract one from the other, and you've got light from the planet in isolation. And that's what we call an occultation. So that's how we're able to tell that.
Oh, by the way, just a small fact in there, that it's very dangerous to subtract and explore the difference between two large numbers. So you're very So David, your confidence in those results, you have to be very sure that you're getting what you're looking for there.
Me published subsequent work that ended up with the same result. So we feel pretty confident about that result.
So Chuck, you notice it's not him reconfirming his own results, because what good would that be? Right. The whole point of peer review and multiple studies, that's how science moves.
Long ago, I was impressed by a professional astronomer who was studying eclipsing binary stars. I was and am amazed by how much info one can extract with careful measurements and clever bootstrapping. Now we are using the same techniques on exoplanets, and the James Webb Space Telescope adds spectral measurements of atmospheres. Could you give a brief summary of what and how we can get details from eclipsing systems?
So Gene wanted to know what methods, tools, and tactics were borrowed from eclipsing binaries to serve your cottage industry of cold worlds.
Yeah, an enormous amount. I mean, there's, in fact, so many astronomers moved from that field of eclipsing binaries into the study of planets directly. That was the transition around the mid-90s when we first started finding planets. There's a really beautiful quote from Henry Norris Russell from 1953, I think he wrote this, that eclipses are the royal road to success. And they're kind of a shortcut. They provide you, it's almost like a cheat code in the universe. For some reason, when these eclipses happen, it's possible to learn so much more about these planets than your technology would seem to enable. Like, we can measure potentially the existence of moons, as we've already talked about. You can measure the atmosphere of the planets. You could look for rings. You could even measure the oblateness, whether it's spherical or football shaped of a planet from those light curves. You can measure the surface reflectivity, as we've talked about, these dark planets. There's an almost endless list of wonderful gems.
The eclipses also enable you to see light from the star move through the atmosphere and then do spectroscopic studies.
Correct. And that's what, gases. Of course, we're all excited about with JWST. It's enabling. So essentially, when the planet passes in front, the same thing as the planet passing in front of the star, some of the light will hit the bulk of the planet, if you like, and hit the solid surface, and that's never going to reach us. That's the shadow. But some of it will pass through the atmosphere. And if it passes through the atmosphere, only a fraction of it will reach us. And the fraction which reaches us will be different at different wavelengths, different colors. So our sky is blue. And so the Earth's atmosphere looks bigger in blue light. It scatters blue more than it scatters red. So an alien looking at the Earth and measuring our size would think that the Earth was a little bit bigger at blue wavelengths of light than it was in red wavelengths of light, because of Rayleigh scattering, because our sky is blue. And they'd even be able to tell that from afar. And go a bit further, you can get the chemicals, you can get oxygen, you can get carbon dioxide, nitrogen. So you can actually figure out a lot about an exoplanet.
All from eclipses. Henry Norris Russell was at one point the chair of the Department of Astrophysics at Princeton University.
That's
Henry
right.
Norris Russell. And the real geeks out there might have heard of the Hertzsprung-Russell diagram. That's the same Russell for that diagram. You can Google it, Hertzsprung-Russell diagram. Okay. Yeah, HR diagram for short, the affectionate term for it. So Gene was right to realize that this trove of information brought to us from eclipsing binaries continues in the field of exoplanets whenever you have eclipses.
There's a legacy, but it goes even beyond that. I mean, when you look at the theory that we borrowed from eclipsing binaries, and I studied this like COPAL, was one of the founders of understanding elliptical orbits and modeling the durations of the eclipses, the timing precession, the secular, all this kind of complicated celestial mechanics was all figured out for eclipsing binaries. So we took that and we still use it in exoplanets, but then we've gone further because, of course, we're measuring atmospheres, we're planetary atmospheres, and stars, they have atmospheres, but they're not nearly as interesting as the atmospheres of planets and all the rich chemical, molecular chemistry that can happen inside them. So
I don't think the stars would agree with you on that.
Then we actually understand stars far better than we understand planets. You know, we don't really understand what's going on inside most planets or how their atmospheres work, how clouds work even on other planets. But, you know, we feel like we have a fairly good understanding of the interior of stars.
Right, because clouds can be made of things other than water vapor, right? Yeah, you can have methane clouds, right?
Could the asteroid and Kuiper belts be considered rings of the sun? So you got the asteroid belt, the Kuiper belt.
Well, Saturn has rings, and it's flat, and it's all around. And so we got these two belts here. What are you thinking, David?
Yeah, I mean, rocky rings, sure, you could call them that. I mean, it is possible that planets could have rocky rings. So if you're going to call rocky rings around planets rings, I don't see why you couldn't call rocky ring structures around stars the same thing. Sure, you know, it's the question is how concentrated does it get? Because normally they form almost like discs rather than or annuli. They're not often so narrow. So I guess it depends on your structure. There is actually an exoplanet that was discovered that has a ring system that forces us to tackle this weird thing of definition. It was discovered by the WASP survey. I think it was like J1407b was the name, and it has a ring system that is.
Well, but just WASP is it's a planet survey, right? So
correct. It's just small cameras. It's just small.
Yeah, it's a consortium of small cameras. And what is the acronym? It's Wide Area Search for Planets, something like that.
That sounds right. This particular planet, discovered by WASP, has this gigantic ring system that is about the same. It's about 1 AU across. That's about the Earth's orbit around the sun. It's like that's how large the ring structure around this exoplanet is. This exoplanet is very, very far from its star, and it has a gargantuan sized ring system, and there's huge cavities in it. And I've seen artist illustrations of this. Now that you're mentioning it, yeah, it's a stunning thing. How does it keep a stable ring while it's orbiting the star? It's very. We don't even know if it is orbiting the star. There's only one eclipse of this thing ever seen, which is where the evidence for the rings come from. It may have just been a chance coincidence that it passed in front of a star. And it was free floating, as far as we know. Okay, interesting. It could be a brown dwarf. It could even be a small star, perhaps. So there's an awful lot we don't know about this particular case. We just have this one snapshot with this rich, apparent like ring system, and that's a good point where we don't know. It's so different to Saturn. What do you call that? Is it a planetary ring system, or is it a circumplanetary disk, which is a completely different category normally of how we think about these things that evolve around planets. So Jupiter, when it formed its moons, probably at one point had a disk around it, and from that disk formed the moons. Is this something like that? Or is it more like something like an ancient ring system, more similar to Saturn? And so it's hard. Classification is hard. And if you want to classify the asteroid belt that way, I wouldn't dismiss it. Yeah, I think that's a fair way to call it.
Okay, cool.
What are the major interesting astronomical events that we can expect with respect to exoplanets for the coming year?
I'm excited. Let's see what I'm excited about. There's obviously JWST is in the sky observing exoplanets right now, and it's observing TRAPPIST-1, which is one of the most fascinating exoplanetary systems we've ever discovered. It probably won't be sensitive enough to detect signs of life on those planets, but it could perhaps tell us whether these planets have an atmosphere that is similar. And these are rocky planets in the habitable zone of their stars. It could tell us whether these planets have an atmosphere similar to a primordial Earth. When the Earth was first born, it was probably a CO2-rich atmosphere. It could detect that quite easily. It could detect a methane-rich atmosphere. It probably can't go all the way to detecting oxygen on these planets, but it's going to be our first glimpse of the chemical composition of a habitable rocky planet's atmosphere. And that's going to come in the next year, 2 years from JDRST.
Wait, how many? Isn't that a multi-planet system? How many planets are in that
There's seven,
system?
at least seven.
Crazy.
Earth-size, in fact, slightly sub-Earth-sized planets
Crazy.
in that system. The seven dwarfs, they're all packed very, very close to this M dwarf, all within the orbit of Mercury, I think, all seven of them. So very, very compact system.
Wow.
So that's very exciting. Then we have Plato, which is a European mission, which is coming down the pipe. I think that's Plato, yeah, after the philosopher. Yeah, so that's in 2026, I think. We're expecting a launch. That's like a super Kepler or even a super TESS. These are two missions which NASA launched to hunt for planets by eclipses. Plato is doing the same thing on steroids. And then down the road, we have WFIRST, which is this old spy satellite, which was given to NASA. And it's basically a Hubble-sized mirror that the NSA were just like, we don't need this anymore because it's such old technology. You can have it and do something with it. So we've repurposed it and launching it as basically a Hubble-class telescope that will do all sorts of stuff, including some exoplanet science, using a technique called gravitational microlensing. So it should find thousands of objects using this technique. So we're very excited about that. And then, of course, you've got Vera Rubin, formerly known as LSST, which is not really an exoplanet mission per se, but I think it could do some interesting things in terms of detecting planets around white dwarf stars. So the sun will eventually become a white dwarf star when it dies. And LSST, we wrote a paper about that in my team, we think could be the perfect telescope to detect thousands of rocky planets, even smaller than that, even asteroid-sized things around these white dwarfs.
If we found biosignatures on an exoplanet, what would be our next course of action, considering they're so far away?
The immediate reaction I have would be skepticism, because I think we're all going to be dubious. So the first question is it real? Because we had a biosignature detection already on Venus, right? Remember that? There was phosphine.
I remember that, phosphine, yeah.
And that's the reaction that played out after that is probably similar to the reaction that will play out for an exoplanet. Obviously, it's a very, we can actually visit Venus. We could actually potentially go there and do a better job. But the skepticism that happened, I think, will be similar to the skepticism that happens with an exoplanet claim.
Well, just in all fairness to the Venus skepticism, that would have been life somehow thriving in Venus's atmosphere, whereas these other signatures would presumably indicate surface life. Right.
Also, I mean, we won't even know. I mean, if we detect a biosignature, we don't know where that life is. It could be in the ocean and the gases come up. It could be on the surface. It could be some kind of whale that floats through the clouds. There's no way of telling from the gases alone. And in fact, it might not. So the two questions: is the signal real? Can another team get it? Which has obviously been some problems with Venus with phosphine. And then two, even if it is real, does that actually mean it's life? Because there are ways that nature can produce biosignatures without biology and just trip you up. So there'll be a decade of arguing and follow-up observations and debates, and it'll get heated of people trying to figure out what's really going on. And there'll be some false starts. I guarantee you there'll be several biosignature claims that will just not be real. But that's okay. That's how science works. Science works through, we're not dogmatic. It's corrective. We're allowed to make mistakes and fix it. And that's science at its healthiest. So just expect that down the road. But eventually, it would be great if we could one day start imaging these planets, maybe building something like LUVOIR or HabEx that people have been talking about, these kind of supersized telescopes that could image the pale blue dots from many light years away. Achieve Sagan's dream of a pale blue dot from across an entirely different star system. And then after that, we'll be trying to just learn more and more about it. Does it have moons? What's the continental structure like? How much water does it have? We'll do as much as we can remotely. And perhaps in the distant future, we might be able to send something, but it's certainly not something within our capabilities in the near future.
Tell me, what are some of your challenges? How much of what you do is theory or modeling or observations? What telescopes do you use? Or do you have a favorite spot in the universe? Are you using Kepler data? What feeds your operation?
It's a big bag of all sorts of stuff, to be honest. I mean, I'm kind of glad that you didn't ask, are you a theorist or an observer? Because I really don't like labels like that. I kind of feel like if you call yourself an observer, and someone who goes to the telescope and looks for different objects in the sky, it kind of limits your mind space, right? So now you think, well, I can't do the hard theory stuff because I'm an observer, and vice versa. I try to keep my feet sort of in every pocket as I can to try and stay nimble. But the data set we're excited about at the moment is JWST, of course, like many people. That's the...
So JWST is touching everybody.
Yeah.
So it's infrared data of what objects?
The observations we're planning in October will be of a Kepler planet, actually, called Kepler 167e. Just rolls off the tongue.
Why Kepler? Why is it Kepler?
Kepler was great for finding cool worlds, actually, because it was very patient. So it stared at the same...
Kepler's been dead for 400 years.
Not Johannes Kepler. So this planet was discovered by the Kepler mission, I should say, the NASA Kepler mission. And it was a planet actually I discovered, curiously enough. And it turns out this is pretty much the best planet for looking for exomoons out there. It is a exomoons. It is a Jupiter twin. It has the same mass as Jupiter within 1%, the same radius within 5%, has the same equilibrium temperature. It's the same kind of coldness, if you like, as Jupiter. It's in a similar kind of system, a multi-planet system on a circle. Everything's just like boom, boom, boom. Everything looks like Jupiter.
And Jupiter has a bajillion moons of its own, and so presumably that's the case here.
Yeah.
So can I ask maybe a dumb question?
Well, I just want to emphasize here that you're about to make progress using a telescope that is building on the progress of a previous telescope.
That's right.
Right.
Yeah. I'm at the end of this is a 12-year personal journey trying to find these exomoons for me at this point.
So cool.
We're still waiting. We're hoping this is going to be the one.
So this is my question about exomoons. So now when you're looking at the planet, it's pretty easy because you're looking for it to transit the star.
Yeah.
Now, if that's how you're finding the planet...
Because that's how Kepler found all of its planets.
If Kepler found all
the transit, the eclipse, it was in front.
Are you looking for the reflection of light off the planet for the moon to transit in front of the planet? Or are you looking for the moon itself to also transit the star? Where is the blockage of light that lets you know that this is indeed a moon?
You kind of said it. We look for the shadow of the moon in front of the star. So if the planet, it's its shadow really that blocks out starlight. That gives us this dip in starlight.
Right.
If there's a moon there, it will either be trailing or behind. And so we'll see this little extra dip in light.
Oh.
And it's that. So we see two dips, one huge one due to the planet.
Right.
And then we zoom right in on that data and hopefully we see a tiny little one.
And then you know
due
that's
to the moon. Or even maybe multiple dips, of course.
Right.
Yeah, but wait a minute.
Wow.
Okay, so you're in a cool worlds lab, but all you're getting here is a cool shadow.
Yeah, right.
And I feel like Plato's cave right now. You don't know jack about the object that's making that shadow.
No, it's a limited technique. I mean, what we get from this is essentially the size of the object. We can't figure out how far away from its planet it is, its semi-major axis. And maybe we could figure out some other things, such as its orbital period, its inclination. So just the bare bones.
The bare bones. That's not a world yet to me.
No.
A world is what's going on the surface.
Yeah, but we will get there. I mean, we're hoping to build telescopes like the Habitable Worlds Observatory, HWO, which might get rebranded one day to something else, perhaps like Carl Sagan Observatory or something. But this telescope will take actual photos of planets one day. And so then we really would get a sense of its color, its atmosphere, and maybe even some surface properties. So we'll get there, but it's all baby steps. You know, you can't just jump straight to the end.
To see dinosaurs walking on it.
No.
Okay.
You'd need a telescope even larger than the sun.
In your studies, you've worked with the concept of occultations to detect exomoons and planets. Could you paint us a picture of how this works? And are these the most important cosmic breadcrumbs according to you?
There was a famous astronomer, Henry Norris Russell, in the 20th century. He once said that eclipses are the royal road to success. It just goes to show you how eclipses are like a shortcut. They allow us to see things that's kind of ahead of our technology yet. Like we shouldn't have the ability really to know anything about 5,000 exoplanets because we can barely take images of nearby planets. It's still something we're struggling to do. But using this trick of seeing a planet pass in front of a star, it gives us an extra window, and it only works in some cases. You have to have just the right alignments. You have to be lucky. But when you get that lucky fortuitous alignment, it gives you this unique ability to probe all these extra things like the period, the semi-major axis, the size of the planet. So it's our first look at these things.
Just to be clear, you're only seeing systems that happen to be edge on to your field of view. None of the other systems are going to give you these eclipses, these transit phenomenon. And so they go undiscussed, unrecognized, uncatalogued.
For now. We'll get them one day.
Look at
There's a
that.
man
Well, of course,
with
we can get some of those using other methods. So,
other methods.
for instance, the radial velocity method has also been very successful. Not as successful as transits, but that's discovered hundreds of planets
Well,
in
now
its
you
own
have to
right.
tell us what the radial velocity method is.
So this is wobbling stars. So as you see, if you look at a star's light and you see it being blue shifted a little bit, then periodically red shifted, that is telling you it is moving back and forth. When it's blue shifted, it's coming towards you, red shifted away from you. So it's just like the siren of the ambulance going down the street. When we hear that pitch change or really see a pitch change in the color of the light of the star, that is telling us that something gravitationally is tugging on that object. And that's how we can infer planets indirectly. So there you don't need the precise alignment, although if it was completely 90 degrees off, we would see nothing, because then the star would be doing this, it kind of wobbling in the plane, and so we wouldn't have any blue shift or red shift to
It's
look
not
at.
coming towards you or away from you.
Yeah, exactly.
Right. Okay.
But most of the time we can still get that.
I think what we have in our favor, because I did this calculation now 30 years ago, if you do this, you are statistically more likely to discover edge-on systems than face-on systems, if you do the math on that.
One thing that I have been pondering lately is the birth of our star, the sun. It seems like a lot of talk happens about when the sun dies. What I would like to know is, was our sun born in a star nursery? And if so, would we know which one, or be able to predict where it might have been or come from in the Milky Way galaxy?
That's a really intriguing question. And it's a question that I know many of my colleagues are thinking very hard about, even at Columbia. So, you know, of course, the sun must have been born, we think, in a stellar nursery.
Okay.
And so there would have been siblings born alongside with us from that giant molecular cloud that collapsed and fragmented and formed all these small stars. We don't know exactly how many, but there's probably many such stars. And the question is, what happened to them? Over billions of years, the stars will disperse. They'll move into slightly separate directions, and especially because of tidal forces from the galaxy, they'll get kind of pulled apart and could be essentially long-lost siblings at this point, you know, spread across half the galaxy or more.
And the sun, given its age and its speed, it's been around the center 20 times. And so if it had a whole family 20 times around, given everything you just said, that can happen en route, you know, your siblings are long gone.
So a family reunion might be possible, at least in a sense of discovering them, by actually looking at the chemistry of those stars. So there is an active effort to measure the detailed chemistry, the abundances of every single element you can think of inside these stars, and compare them to that of our sun. And these sibling stars should have not only the same age, of course, but also the same chemistry.
So a gas cloud not that far away would still have all these elements, but not in the exact amounts relative to each other.
Yes.
So that's like a fingerprint.
Yes, exactly.
All right.
Yeah. I don't know the latest on that, but I know that there are many astronomers who are hunting hard for those. And I think we'll probably hear big news when they're discovered.
Let me restate that question, but in another kind of way, because we can't see the birth of the sun, it having happened in our past.
Yeah.
How much insight are we getting now that we can see stars being born with their planets? How much insight from these other systems do we then bring back to ours?
There are some startling things we've discovered. I mean, one thing from direct imaging, which is actually taking photos of these young planetary systems in the process of forming planets.
Catching in the act.
Right.
Yep.
I mean, they're very young, hundreds of millions of years old or less.
That's young.
That's young in cosmic terms.
Okay.
One thing that's very startling about these is we see, you know, I mentioned earlier that Jupiters are rare, but that's in mature systems. In these young systems, we actually do find lots of Jupiters. And what's strange is that they're really, really far from their star. They're on order of hundreds of AU. So an AU is the Earth's orbit around the sun. So, you know,
astronomical unit.
Yes. Jupiter is 5 AU. Saturn, I think, is about 10 AU. So these things are 10 times more than that. They're sort of the distance where we talk about looking for Planet 9. And we're discovering Jupiters very often that far out. And they're very massive. They're actually bordering on brown dwarfs, which are like sort of 10 to 20 times the mass of Jupiter. And that is a mystery. It's, you know, maybe the solar system then also formed such planets, but they were somehow lost, because these things are so far out that they're maybe tenuously held gravitationally and would be stripped away. And there's an active...
So they would be, what do we call them, vagabond planets?
Rogue worlds,
rogue
yes,
planets.
free-floating planets. Recently there's discovery of what's called jumbos, which is pretty interesting. These are Jupiter binary... Jupiter binary mass objects, I think. So these are 2 Jupiters, and these are free floating. So not just one Jupiter hanging out in space by itself, but 2 of them orbiting around each other. And we can understand how maybe one Jupiter could get kicked out of its solar system, But how the hell do you end up with two bound to each other?
And they're right, and they're together.
Yeah,
yeah.
that's so weird. We don't
Those are called
understand
jumbos.
those. Those are
The
jumbos.
pair is called a
Recently
jumbo.
discovered by JWST in the Uranus Nebula.
What's the fastest rotating star we have found per pre-nova? And what would hypothetically be the fastest possible? How does this rotation affect the star's atmosphere, fusion, and life cycle?
Stars all spin. The sun is spinning. I think its rotation period is about once every 27 days, something like that. And that's not untypical. Many stars have similar rotation periods, but they change their spin over time. So they actually tend to spin down. So again, if we go back in time to when the sun was young, it would have been probably spinning much, much faster and probably arguably close to its breakup speed. So there's a certain speed called breakup speed where it's rotating so fast that the centrifugal forces outwards are comparable to the gravitational forces inwards. So stars are probably, when they're very young, have these extreme rotation speeds. One thing I actually learned from one of your colleagues right here at the Museum of Natural History on my podcast, and the Cool Worlds podcast, we had Jackie Fatty on my podcast. And
Jackie Faraday, yeah.
Yeah, she was telling me that some of the brown dwarfs are rotating close to that kind of breakup speed as well, and they seem to have rotation periods of order of hours, which is incredibly fast. And they're essentially almost stars. They're just below the masses of stars.
Failed stars.
So it's interesting. Why do those brown dwarfs, which are presumably quite old in many cases, still got their rotation, and the sun has lost most of its rotation? And we think it's probably from an effect called magnetic braking. So the sun has this strong magnetic field, and from that magnetic field, it accelerates ions and particles along those field lines, and they basically get kind of ejected out of the solar system. And once they kind of leave the heliopause and get really far away from the solar system, they essentially decouple from those field lines, and then they just carry away what's called angular momentum, spin energy, essentially, from the sun. So the sun basically, by throwing stuff out, imagine you're on a merry-go-round, and you're spinning really fast. And if you start throwing stuff in the opposite direction to your direction of spin, you could slow yourself down. Right. And it's kind of doing the same thing. And so over time, these stars break and slow down. And we can actually even use that effect.
You call it magnetic braking.
Magnetic braking. I was going to say Ruth Angus, who's here at the museum as well.
Ruth, another museum. Right here at the Museum of Natural History.
Yeah, you guys have the
Department of Astrophysics. We got some good people.
Good people. Yeah. And she's been showing that you can use this to age stars. So you can actually use the speed to figure out how old the star is.
To age date them.
Yeah.
Yeah.
Yeah, it's called gyrochronology. Wonderful.
Gyrochronology. I love it.
Since we've upgraded from the Hubble Space Telescope to the James Webb Space Telescope in our orbit, will we eventually upgrade again? If we do, what would be the goal of the new telescope, and what would be expected of it for discovery?
People are thinking about that really hard right now, and it seems like a lot of people are converging around the idea of some kind of direct imaging mission. So we want to actually take photos of these distant exoplanets. And the leading candidate that people are currently converging on is called the Habitable Worlds Observatory, HWO, and it may be rebranded. We'll see. I don't really like that name too much at the moment, but it might be rebranded. And the plan is to build something that's about 6 meters is what the decadal survey recommended. This is every 10 years, astronomers come together and they all pitch in their ideas and try to converge upon what they think the best ideas are. And the one that
That's why you rarely see us fighting with each other about what should get funded. Because we go through this very elaborate process. Speaking of the decadal surveys, has the Habitable Worlds Observatory showed up in one of them yet?
Yeah, it was the top recommendation in the last decadal
in the most recent one. And JWST would have been in previous ones.
Yeah.
So they're coming in.
And Hubble before that.
And a decade or two before the real thing happens. So anyone wants to eavesdrop on what we're thinking.
Right.
That's how you do it.
I kind of like that though, because you're zooming in with each one. So each iteration is a closer look of what's out there. So it kind of makes sense in terms of the progression.
Yeah, and this is, by the way, just what we call the flagship missions.
JWST, because it's the infrared and because it was conceived to be able to observe the birth of galaxies, which in the early universe emitted ultraviolet, but then redshifted to the infrared in today's epoch. But the infrared also lets you see inside gas clouds. So JWST is serving early universe astrophysicists as well as looking into gas clouds that are sitting in front of our nose. I ask you, JWST serves many branches of astrophysics, people who would not otherwise ever be talking to one another in their research projects. Does this next generation flagship mission also serve people who are studying large-scale universe? Or is it just your people who are studying habitable worlds?
I think we'll see, but obviously the primary focus is imaging exoplanets, but that also means it has amazing abilities, for example, to image stuff in the solar system. And depends whether you call that a separate field, but planetary scientists and exoplanetary scientists actually tend not to talk to each other too much. On top of that, it will hopefully have ultraviolet capability. So when you go to the ultraviolet rather than the infrared, that gives you access to that high energy universe.
Yes, it does. Like black holes and stuff.
Yeah.
Yeah, good.
So I think in that sense, it will be.
I'm glad to hear that, because one of the great things about JWST is because of how many different branches, how many different subfields within astrophysics it serves.
Correct. Yeah.
Yeah. As did Hubble.
Yeah. We want this. We want, if you're going to put a mission of this kind of price tag up there, you want the whole community behind it. So you can't just go singly on a single
It's
goal.
billions price tag. But the smaller missions are how much? Just
maybe $100 million.
$100 million, yeah. Just.
My question is about luminous fast blue optical transients, or LFBOTs. Have astronomers, astrophysicists come to the determination as to what they are? Is it a supernova, kilonova, intermediate black hole shredding a star? Also, why do you think that the LFBOTs are so different than others, or one particular one, which is AT2002?
I haven't heard of these. Do you know anything about them?
I don't know a lot about this particular phenomena, to be honest, but I think it's another example similar to this is sort of fast radio bursts, where there's these very strange observations which we still don't really have a good explanation for. I think it's just a nice example, I would say, of the fact that there is still a huge amount about the universe that astronomers do not agree about what's really going on, and that's kind of what makes astronomy interesting.
That's what's great. What are the elements that are made in stars?
Why are we made of star stuff?
Why?
Because
let me preface that.
Yeah.
These cool worlds you're looking for, can I presume that some of the motivation is there might be places where you'd find life?
Oh yeah, for sure.
Okay.
That's one of the main reasons we're interested.
Otherwise, it's just an object out there.
Yeah.
Okay, so you should then care deeply about the ingredients of life.
Correct.
Okay,
yeah,
good.
and the search for it. Yeah. So I would just put it like this: like there isn't really that many ways to make heavy metals, what we call metals, heavy atoms inside your body, inside planets, and stars are the main manufacturing method which the universe creates these things. So why we star stuff is because there's basically no other way to make the stuff in your room and in your body without having a star. It's all manufactured inside the core of those stars.
Ooh. All right.
And so you care that all those same ingredients are on your cool world.
Absolutely. Yeah. I mean, what we're hoping is to detect those molecules in exoplanet atmospheres, which will be our first hint of complex chemistry and life potentially in those planets.
There you go.
We don't know that all moons have a frozen core because we only know about the moons in our own solar system. What about the moons out there in the rest of the universe? And then you've got moons like Io, which are being actively squished and squashed due to the gravity and the tidal field
Jupiter.
from around Jupiter, exactly.
Right.
So it's not obvious that Io would have a frozen core either because of all the tidal deformation it's going under. And we know it certainly has volcanism, so it must have some layer of magma underneath its surface.
But would any moon have a frozen core if it collapsed from something bigger? Doesn't it get hotter in the middle? So wouldn't everything be...
But over time,
then
it'll cool.
It could cool to just being a rock floating and boom, frozen. And that's it. How common is it for planets to have atypical rotations? Do they always occur?
Atypical, like not typical?
As in, atypical, as in not, right, atypical. Do they always occur due to external forces? Can it happen to other astronomical bodies? Have we observed a planet that rotates in the same odd manner as Uranus, but in the opposite direction?
Ooh, maybe they're also referencing the orbit.
Right.
But there's rotation and revolution.
Revolution and rotation.
Right, counter rotating and counter revolving.
Right.
That's if they exist, they should be showing up in your data.
Yeah, so in terms of the orbit, yes, we can measure that. We can tell if it's going backwards around its star. And there are some cases we use this effect called the Ross-to-McLaughlin effect that essentially looks at the redshift and blueshift of patches of the surface of the star as the planet passes in front of it. Using this effect, you can actually tell which way the planet is going over the face of the star by looking at those little shifts.
Whoa.
We have these clues and we have to think really hard about unpiecing what's going on. So, you know, with the rotation in terms of orbit, we can get that. The rotation in terms of the actual planet spin, we can't measure that. There's only been measured, I think, for one planet, and that's Beta Pictoris b, and that's a directly imaged planet. And in that case, it looked kind of normal, but that's the only example we have. So it's actually something we're working really hard in the future of these new telescopes to try and measure.
So beta is the Greek sequence of the lettered stars. And for many constellations, it's lettered in sequence of brightest to dimmest. So there'd be Alpha Pictoris, and then Beta Pictoris would ostensibly be the second brightest star. So Pictoris is the genitive form of pictor, which is a painter's easel. That's a constellation, a painter's easel. And then your regular letter, your Roman letter was what?
B.
B, lowercase b.
Yes.
And
that's the first planet discovered. Right?
The first planet discovered around it. And A you give to the star itself. The star itself. Yeah. Okay. Yeah. And so who's got the most planets out there?
TRAPPIST-1 is a very famous star system that has 7, sometimes called the 7 dwarfs, because they're all such small rocky planets.
Okay.
But I think there is another star that has 8 planets that's been discovered, but that's just what we know of. So there surely are even more that
you know what would make headlines? If he discovers one that has 9 planets, the Pluto people will rise up. Well, let me reflect on this briefly, and then we call it quits. Okay. All right? So every generation of telescopes, we're trying to answer questions that we've posed. But you know what happens? Those questions and our attempts to answer them take us up to the limits of what that telescope can deliver. And those are the seeds for a next layer of creative thinking about what science can be discovered and what new tools and technology may be necessary to discover it. At any given moment, we have smart people and great technology trying to figure out how this world works. But there comes a time where the technology can only take you so far. Maybe there are questions you had but remained unanswered because you're awaiting a next generation of technologies to get you there. And maybe you're awaiting more than that. Maybe you're awaiting a next generation of thinkers, students you have trained that will come after you and carry on questions that you've begun. Or better yet, maybe with new technologies, new science, new ways of thinking, there are questions you will ask that you didn't even know to pose. So when I think of David Kipping's efforts with the James Webb Space Telescope, there's some questions he couldn't answer with previous technology. He tried, couldn't answer. Now they're flowing. But what happens next? He sees things that are at the edge of what this technology can deliver. And now he's looking to the horizon. Is there another kind of telescope that can hone in on these unanswered questions? And maybe that'll take me there. And you step back and you see this exercise and you say, that's how science works. One idea builds on another. One bit of technology surpasses what came before it, enabling you to answer questions you have posed and to pose questions you never thought to ask. I wouldn't have it any other way. That is a cosmic perspective. Thank you for being on StarTalk, dude.
It's my pleasure. Thanks.
You just right up the street. Today we're talking about the physics of monsters. I got with me Matt Kirshen. So this monster subject, you know, I have some interest in the physics of monsters, but when we hit topics like that, we've got to call the geek in chief. You're a professor at CUNY, Staten Island.
Yes.
CUNY City University of New York.
Yes.
Many campuses in the city.
25.
Oh my gosh.
250,000 full-time students.
Wow.
Yeah, it's a great system.
And you have a podcast that started a few years ago.
Yes.
The Luniverse.
The Luniverse.
I see what you did there.
It wasn't me, okay? My family did. I'm proud to have it as the name, but I always thought it was a little bit weird to put your name into the universe and claim that you had any real role.
Almost everybody's podcast has their own name in it.
Yeah.
So don't be afraid of that.
Okay.
So the physics of monsters.
Yes.
Gosh, that topic has no end.
No, it has no end whatsoever.
And monsters, there may be actual animals in our environment that we didn't know much about and only showed up at night. Maybe had beady eyes, and people, maybe they worked their way into legends as monsters.
Yes.
And one of my favorite is it the Triceratops skeleton that was coming out of some eroded cliff face?
Yeah.
It was like, what animal is this?
That's right.
Is this a dragon? Before anyone had any understanding of dinosaurs or extinction or anything.
Yeah. There's a famous, I don't know, human nature makes us think about monsters, because when we have something that's unknown and we fear it, we want to explain it. We want to put it in a context. And so with me, as a professional scientist, I still am driven by the unknown and the creative and the strange things.
As you must be if you're going to be a good scientist.
Yeah, I love comic books. I love science fiction and fantasy and everything like that. And what we did as a species centuries or millennia ago, anything we didn't know, didn't understand, and feared, we tried to personify or put into this concept of a monster, make it more accessible to us. And then years later, as we have learned more about our natural world, we see that those monsters aren't monstrous at all. In fact, they're very natural, and it's scientific. And that kind of connection and learning about these creative things makes us feel cooler and makes us feel better about the whole universe.
So do you have a favorite monster? We all do, presumably.
At the moment, my favorite monster is Godzilla. It is the longest running movie franchise of all time. The first Godzilla movie came out in 1954. So it's been 70 years of Godzilla.
So you're not counting Train coming towards you as a monster? Because that
in the original silent movie.
In the original silent movies, that's right.
Or slowly galloping that.
Well, those are monsters of a different kind, right? Those are the monsters in our imagination. Things that we think are frightened and scary, they must be a monster, but then turns out it's just a train, right? It can still smush you, but it's just a train. Now, the thing about Godzilla, which is extra special to me, is that it can be that kind of subway monster, loud, scary, and it burns you with its atomic breath and everything like that, right? But culturally, when it came to the United States, it took on a different kind of life. You see, in Japan, monsters since time immemorial have not necessarily been these evil, scary creatures. They are just non-human creatures. And as a result, they can be different from humans in ways that you can find in literature, in stories, in mythology, that allows you to tell things, much like the gods of Olympus did, say, in ancient Greek times, about things that we don't understand and are trying to understand, not just of nature, but of human nature.
Going back to Greece and Rome, are you suggesting, for example, that in our 88 constellations of the sky, there are non-human creatures up there that you might think of as a monster? We have centaurs and
we have Draco, the dragon,
Draco the
wrapped
dragon
around the North Star.
Yeah, and we have Minotaur, which is like half bull.
Those are pretty monstrous too, right?
But they're not portrayed as scary. They're just non-human things.
Yes, and that is precisely how I see monsters based on that kind of cultural thing, right?
You have Asian heritage from Taiwan.
Yes, absolutely.
So our exposure to the Asian, if I may group it that way, dragon, is very different from the European dragon.
100%.
The European dragon is a menace.
That's right.
Whereas the Asian dragon is just a playful thing that...
Not only playful, but noble and very helpful and so forth. The constellations of the Chinese zodiac that you know, right?
Yes.
The dragon is kind of in the middle. The story is very long, but to cut it short, the reason it's number 6 as opposed to number 1, because it's such a powerful creature, is because it saw a rabbit in trouble crossing a river. And so he went back to help the rabbit cross the river and let the rabbit finish in the contest before he did. So the rabbit comes before the dragon.
If I remember correctly, from my Chinese zodiac, the dragon is the only non-actual animal of the 12.
It is the one truly mythological creature.
Right.
That's right, in the zodiac. And indeed, dragons are considered particularly successful, particularly smart, particularly potentially wealthy. So people will actually change their birth dates of their children so that they are born in the year of the dragon. They will delay C-sections, they will wait and so forth, just to make sure. This is the kind of thing that I want people to think about when it comes to monsters, right? They're not necessarily good or bad unless we project those facts in. In fact, aren't the true monsters we humans ourselves?
I think it was a deliberate act of naming that on Sesame Street, the Muppets, were all called monsters. But they're lovable and playful and colorful. And so I think it was intended to de-scarify a monster in the eyes of small children.
Is a vampire a monster?
Ooh.
Absolutely it was, right? When the original Vlad right, the Impaler,
Mhm.
right, and was later on died, and then people in Transylvania area, not Transylvania itself, but that area of Eastern Europe wanted to scare their kids. They said, be careful because Vlad will come get you, even though he's dead, right? And the concept of the undead, which had been around for thousands of years in folk mythology, got embodied in this one guy, right, Count Dracula, which was then brought into modern times by Bram Stoker, and then into the movies with Bela Lugosi. So that kind of monstrosity, right, is literally a human being that has become something non-natural. So the evil comes from not the fact that he's not human, but because he used to be a really bad human.
I was simultaneously enlightened and disturbed when I came to this realization that Godzilla in Japan, within 10 years of the dropping of the atomic bombs, shows up as a radioactively influenced,
created.
The radioactivity created him. I was thinking to myself, Japan is the only country against whom atomic weapons have been used.
Yes, this is not a coincidence at all.
That's why I want to affirm here that it became part of their storytelling culture. What are we going to do with this? How are we going to come to terms with it?
Yes.
So again, it's a way of sort of embodying your fears and the worst things that have happened to you.
That's right.
And personifying them.
Think about environmental degradation, right?
Yeah.
The Godzilla was the result of, according to the mythology, atomic testing and the radioactivity that basically awoke a sleeping giant or transformed something that was large and powerful but benign.
You didn't even have to give the specific details of that. Just that there was it created this life form.
Turned it into this terrible thing that destroyed humans. In other words, what did we create?
So destroy
what
cities.
have we done? Oh,
there's city killers. Humans are collateral damage.
But you see, what happened was other monsters like Gamera, big giant flying turtle, by the way, very cool, very similar to Godzilla in size and shape, but different kind of.
Is this also from?
Oh yes,
the
from that Japanese tradition.
What's the name of this one?
Gamera.
How come I know? I don't remember Gamera.
Oh,
I remember Mothra.
Mothra, yes, who attacked Gamera also, would sprinkle little things onto Godzilla and confuse him.
But my favorite, can I say my favorite?
Yes.
But I want to keep telling me about Godzilla. I just have to get my favorite out.
Get your favorite.
My favorite was Rodan.
Pterodactyl is just
because
flying
it was supersonic.
Okay.
It would like fly and trucks would tumble in its
wake.
In its wake.
That's right. Yeah. Before Mothra became a butterfly, Mothra was a caterpillar who flew.
I thought Mothra was a moth.
Mothra became a moth after, but originally Mothra was larval, and like nature, right before achieving the flying state, was a caterpillar, a silkworm, literally flew out.
Silkworm
lots
again.
And lots
you
of
get
stuff.
the regional culture.
That's right. And so there was actually one of the great monster movies of all time. It was a collab. They had Godzilla, Mothra, and Rodan together to fight King Ghidorah, which had 3 heads and was very, very dangerous and was like brought in from alien. King Ghidorah was not a product of Earth. It was an evil monster.
Wasn't there an episode? Wasn't there one of these movies where Mothra as a caterpillar spins a cocoon to trap the enemy monster?
Oh, many episodes.
Oh, many episodes. Okay,
many things like that.
Just
yes,
the one I saw.
And in fact, there's episodes. We keep calling it episodes, but they're just individual movies. But the franchises have become so huge that they're almost like individual episodes. But at least in one movie that I saw a long time ago, I don't remember the exact details of it, the eggs hatched and there were 2 new Mothras. The scientist says knowingly, yes, multiple births are common in the natural world, or the insect world, or whichever world it was he was talking about. But that kind of connection between these monsters being representations of nature, something like King Ghidorah, which is the representation of evil and conquest, right, wound up coming against each other. And monsters like Godzilla, which wiped out cities in early episodes or early movies, wound up saving humanity more than once, including, ironically, against humans creating a new monster because of environmental degradation, not nuclear, but pollution. Famous movie, Godzilla versus the Smog Monster. Well, Godzilla's difference from just a big dinosaur is his atomic breath, right? And the physics of the atomic breath have been retconned over and over again. How does he breathe fire, right? How does he breathe this terrible
Weren't
stuff?
dragons breathing fire before Godzilla did?
Yes.
But here, this is a different account.
And
That's
also,
right.
presumably, the myth of dragons breathing fire long predates any human knowledge of atomic energy.
That's
Yes,
right. That's
yes.
right. And so the idea that this fire comes from that is very important, and it's atomic in nature. But Gamera, that turtle guy I was referring to earlier,
A flying turtle.
yes, actually not only like catches a child that's falling, like he eats fire. It was figured out in the first Gamera movie that the reason he was destroying cities was because he was seeking fire and he wanted to eat it because he needs that. That's his nutrition. And so when he knocked over a structure where a little child was watching and it was like the child was going to fall to his death, Gamera caught the child, put it down. It then literally was willing to leave the world to save Earth. What happened was the humans said, we want Gamera to survive. Gamera's obviously not evil, but he can't come around and knock down our cities and eat our oil refineries. And so they created something called Plan
You said
Z.
he eats fires. Yeah, he eats,
like Plan Z. Okay. And they had him stalled at a train depot and just kept sending trucks and train cars full of gasoline onto him so they would catch fire and so he'd eat the fire. And then they cut that off when they got Plan Z ready. They had all these flares that would slowly get him up a mountain, and they'd walk up the mountain. Okay. But unfortunately, a hurricane came, a typhoon, and blew out all the flares. And so he was like, oh, blasted typhoon. He was gonna head back down to the city, but then the volcano erupted. So he kept going up toward the volcano.
Is this Fujiyama erupted?
I don't remember which mountain.
How many
it was.
volcanoes are there
That's
in
right.
Japan?
Right.
I mean,
But this is just amazing coincidence. You have a typhoon coming and a volcano erupting at the same time. And then he slowly went up to the top, and then he got into an area which had a lot of fire, and then the area closed up and turned into the top part of a rocket, which then sent him to Mars.
in terms of the science of monsters,
Yes.
many of these are derived from actual life forms that are important to us, what we think about and care
Dinosaurs,
about.
for example, in the case
Right.
of Godzilla. Yeah.
One thing I've always had an issue with was to be that large,
Yes.
yet that nimble.
Can't do it.
You can't do that.
Can't do it. No, it's physically impossible. Right?
Yeah, so talk about that.
Well, the scaling of volume and surface area and height, right, goes at different powers. So if I double in height, I'll actually increase by a factor of 8 in volume, right? 2 times 2 times 2, length and width and height.
Ooh.
So I would be 8 times larger in volume. And thus, presumably, all of the stuff inside me is made of the same material. I'm 8 times heavier. That means my legs have to support 8 times the weight, right?
Right.
Now, if I get bigger, it gets worse. If I'm 10 times taller and wider and thicker, then I'm 1,000 times more massive. Okay, my legs are increasing in surface area, in cross-sectional area, only by a factor of 100 in that case.
Right.
So my bones have to be 10 times stronger to support my weight.
Well, because your strength goes not as the volume, but as the area,
That is
cross-sectional
generally
area
true.
of
That's
the
right.
muscle.
Right.
So,
Mhm.
so
And your muscles have to be 10 times stronger to propel them. And
that's
so.
absolutely right. So if Godzilla being 400 feet tall or so in the first movie, all right,
Godzilla will weigh 1 billion tons.
yeah, so much that all known bone would shatter, right? All known muscles would tear. He would just be a blob of protoplasmic stuff because he couldn't support himself. Never mind walking with that cheerful little gait that he has. This is where that creation of monsters like Godzilla get exciting to us, because we do see animals, insects, things like that are smaller than us do amazing superhuman things if they were scaled up to size.
Right.
So we imagine that if they're even bigger than we are, they'd be even more amazing and powerful. But the physics prevents that, right? That doesn't make them any the less cool. And so modern monsters, right, are looking more and more friendly and cuddly, right? Less and less evil and scary.
You're very helpful there. And so I just realized we had a monster earlier than our version of a monster earlier than Godzilla, and that would be King Kong. That's 20 years earlier,
That's
in the
right.
1930s.
That's right. Uh-huh.
Right.
And a giant monkey, ape, chimp type creature, who was benign and perfectly friendly and was living on a Skull Island and doing great until humans decided to take him to New York and show him off as the eighth wonder of the world. And only then did he become bad and harm people.
Right. The movie, now that I'd forgotten this, was quite sympathetic.
It was very much so. It was. Some people think that it was a way that the movie makers were trying to say, "Hey, don't hurt the environment, guys. You know, take good care of nature, lest it comes back and bite you in half." And one of the scary scenes of King Kong, where he actually had a human being in his teeth, but that was sort of nature unfettered if humans messed it up, right? And he wound up being in love with Fay Ray, the girl, climbed up the Empire State Building, and then airplanes came and shot him and killed him, and he fell down to Earth. And the last line of the movie, "'Twas beauty killed the beast." You know, one of the things also was the humans losing control of nature, right? Because
another repeating theme.
That's right. When the reveal of Kong happened in New York City, and the flashbulbs were popping, and he was getting upset, and he was pulling against his restraints, right? Well, the impresario said, "Don't worry, ladies and gentlemen, those shackles are made of chrome steel. There's no way he can break out of those," right? And then he breaks out of them because humans underestimated the power of nature in our hubris.
Another sympathetic monster.
Yes.
But you have to remember that you were sympathetic to him is Frankenstein's monster.
Yes, absolutely.
That, you know, I felt sad for the thing.
Yes, considered by many to be the first true science fiction novel in the European tradition. Percy Bysshe Shelley's wife, Mary Shelley, wrote this book, Frankenstein. It went through several editions in the early 1800s. But the monster was the creation of Dr. Frankenstein. It was an allegory about what happens when you try to violate nature, because he was a man trying to reproduce, trying to create life.
Trying to be God.
Yeah, that's right. Trying to be a woman, trying to give birth to life. And so the combination of just defying nature and defying God caused Mr. Frankenstein, Dr. Frankenstein, to lose control of the monster, and the monster winds up becoming this bad thing.
So comment on the details of how he accomplished this. So he went to graveyards,
yes,
and got body parts that are long dead.
That's right.
And
which at that time was also social taboo.
Yeah, of course.
You weren't supposed to mess with people.
Since Da Vinci's day.
That's right.
Where else is he going to know where all the muscles are? He digs up cadavers in the dark of night.
You're not supposed to do that.
Yeah, and would presume, and that they were grave diggers, grave robbers who they would.
Well, they would take
on the sly.
Well, no, they wouldn't care about your body. They wanted the
jewelry,
right? Yeah. But there were people who would then grave rob and steal for the cadavers, right? For the artists or for the.
So they got a third party to steal.
Well, that came later, sort of in the mid-late 1800s.
So what I'm getting at is the idea that the body is absent some life force.
Yes.
Okay, and you can't have electricity in your novel until electricity has been discovered.
That's right.
As a thing that you can harness. Right. And so do you remember the exact year of the
1817, 1818, I think, is the first edition.
Okay, so Ben Franklin was active with electricity.
By then,
at the
Ben
time.
Franklin had already figured out plenty of electricity.
Yeah.
And at that time, guys like Galvani, right, Alessandro Volta, these guys had started attaching electrical connections to like frogs' legs and things like that, and made them twitch.
And therefore realized that there was a connection between human or animal movement and electricity.
Correct. And so now you have Frankenstein with these body parts that no longer have a life force, whatever that was understood to be in the early 19th century.
Reanimated by lightning.
When he stitches it all together, now you take the best source of energy you have available.
That's right.
That's going to be a lightning bolt.
That's right.
And it goes into the electrodes and he becomes animated.
Even at that time in the 1800s, although folks like Benjamin Franklin had already figured out that lightning was electricity, you still had most of the people in Europe and America thinking that lightning was an act of God, that it was the divine something. And you can go back to the ancient Romans and the ancient Greeks who thought that Zeus or Jupiter was throwing thunderbolts down at us. But now that we know that it's lightning and so forth, you kind of remove that monstrosity of Frankenstein being unnatural. Was perfectly natural for that to happen. Another idea of physics eventually informing monstrosity.
Right. So what I like about it is, given the other experiments, like you said, with the frog leg, this is not such a far out idea.
Not at all. Not at all.
At the time.
Yeah, that's right.
And today, what do? Your heart stops. I throw electricity into it.
That's right.
To bring it back.
To get it started. Mary Shelley was actually very prescient.
Percy Shelley was the author.
Percy Shelley was an author, a poet, actually.
That's what it is.
Yes.
Okay.
But Mary Shelley was actually, perhaps in sort of retrospect, the more talented of the two. And Mary Shelley, aside from writing Frankenstein, also wrote an apocalyptic novel about a pandemic that actually killed everybody except a few people. I think it was called The Last Man. I have to check that. I'm sorry, I don't remember exactly the name. At that point, she was speculating about science fiction, about how people could travel from London to Cambridge in a matter of days by balloons that had wings attached to them that were flapping like birds. Really neat ideas. So it was airships. The idea of airships.
So she's, I mean, really, because I knew of her as being considered the sort of formation of science fiction just from Frankenstein. I didn't know that.
Right.
Yeah, all these
many of these other
strings
books
to her bow.
That's right. So she has really good stuff, and she did this all before Jules Verne started doing things like Journey to the Center of the Earth and 20,000 Leagues Under the Sea, and
and to the moon and back. Journey to the Moon. Frankenstein comes back from the dead.
Yes.
The undead is there is no end.
A rich area.
Why is it so rich? I was never as enchanted by the undead as so many other people have been.
That's right. And nowadays, just to sort of contextualize your question, zombies and undead things are indeed the monster du jour, right? On our whether it's the Walking Dead from past years, now there's The Last of Us, even
zombified by fungus.
Zombified by fungus, 28 days, 28 years later, and that kind of thing.
Whether the cause is a virus or a fungus or whatever.
That's right. Things that are not alive fascinate us simply because we're not dead, right? Think about this. Things that are not alive fascinate us because we are alive and we don't understand them.
We have no idea, unless you're religious and you have a strong belief ethic in that.
That's right.
We have no idea what happens after death.
That's right.
Nothing can be spookier.
That's right. And even those belief systems cannot be confirmed in any sort of experimental strategy.
Right.
People have tried. As you know, they're even expressed in fiction, like Dan Brown's novel, Angels and Demons. There supposedly was an experiment where they had somebody who was about to die and weighed him, and then he died, and they weighed him again, and it's a little lighter. Some sort of physical thing,
they even
like
tried
a soul.
And you got to give them credit for doing the experiment.
You got to try.
Yeah. So if everyone thinks you have a soul, and there's science that can test things, why not test your soul? So right after Wilhelm Röntgen discovered X-rays, X-rays can see through your body. No one else ever saw through your body.
Right.
Now X-rays. So they get somebody dying on the bench, and they waited for him to die to see if they saw something leaving his body with the X, and they didn't.
They did not.
Yeah.
That's right.
Yeah.
So there have been continuous experiments to try to understand what it is that makes something alive versus not alive, right? Because a living person and a dead person, seconds apart, for example, right? One moment they're talking, they're breathing, they're whatever, they're holding your hand. Next moment, they're not. And we can't get into their brain to figure out how that works.
An important feature of The Walking Dead, in my judgment, was if you were dead for a long time, so your body was putrefied, you're not going to come back to life.
That's right.
You have to be not so dead that your organs would not be harvestable.
That's right.
By the card that you signed.
That's right.
On your driving license.
Right.
And that's where the transition comes when you become a zombie.
And one other thing about The Walking Dead was that everybody was infected, whether they were dead or alive. The moment you died, you became a zombie. So what's the point of even trying to stay alive when you know you're going to become a zombie anyway? But that's sort of the existential question of what makes a monster and what makes a human, right? If you've died, you automatically become a monster, or do you become inanimate? Are you different from a rock or a steak? And of course, you can do something like what happened in World War Z, where the author said, we actually don't know why these zombies violate the laws of physics so completely. And yet they do. Incredible story. Without ruining, spoiling the story for everybody, basically the army wants to make a big show of force to stop these zombies. And so they bring the soldiers over and they like have all this firepower. Turns out that they're routed by the zombies because the army has not thought through how to stop them. And so again, humans in our hubris thinking that we can control a force of nature when in fact nature comes back and tells us, no, it's not going to happen.
So one feature of sci-fi, which is I think its finest feature when well done, is it's taking place in another place, and yeah, there are aliens and there's rockets and it's in the future, but there's some story element that's a reflection of the time in which you live.
Absolutely.
So that there's
100%.
a lesson in there.
Yes.
Either a moral lesson or a philosophical lesson.
Yes.
So in the zombie storytelling, the zombie genre, I'm almost fatigued wondering, is there more lessons that they can teach? And what lesson was there to start with?
Let's use The Last of Us, which was built originally as a video game, but now has been turned into a very successful
as so many
television
things
series.
have.
That's right. Remind me to tell you about Monster Hunter. Okay, that is a great game franchise, but that's in a moment. Right now, we would say that the reason that The Last of Us happens and humans are threatened, global warming is the culprit in The Last of Us.
I did not remember that fact.
Mushrooms or fungi, okay, particular group of fungi, cordyceps, is there are hundreds of species of this particular fungus.
Let me remind people, fungus is an entire branch in the tree of life.
It's a kingdom.
Right. It's a kingdom.
Yeah.
Yeah, the animal kingdom. When I grew up, there were only two kingdoms.
That's right, animal and plant.
And plant. The fungus is its own kingdom.
Yes.
That's how badass they are.
We now understand that's the case, right?
Yes.
But see, fungi, they can't survive parasitically in humans because we are warm-blooded. We have a higher body temperature than most fungi can tolerate. So fungal parasitism or infection happens all the time in the cold-blooded world. Okay, ants, wasps, they are parasitized by fungus all the time. There's a famous zombie ant fungus that causes the ants to go up, and then the fruiting bodies grow out of their antennae, and then they pop, and then the fungi continue to reproduce, right? And we consider that to be very scary because that doesn't happen to humans. When we get diseases, it's from viruses and bacteria most of the time.
Not from fungus.
But not from fungus.
We get skin to skin fungus.
Yeah. We get little things.
Yeah.
But what happens in the Last of Us mythology is that because of global warming, funguses or fungi start to evolve to be able to live in warmer temperatures. And eventually one of those parasitic fungi, the cordyceps, whatever.
Jump species.
Right? Jump species. And is able to live in humans even though our body temperatures are 98.7.
Not just on the skin.
That's right.
Where it's not
inside.
Body temperature.
And so we basically become parasitized by this fungus. And the fungus is not evil. The fungus is just a fungus. But what happens when humans are now threatened as a species by the fungus? You find out we humans do monstrous things like kill and oppress and push away and isolate and so forth because we are afraid of what we have created from the global warming and from the natural reaction of nature, fungus evolving to thrive in what we create.
You would give zombie storytelling high grades for continuing this tradition of science fiction to hold up a mirror to who and what we are.
Absolutely. Nowadays, right, we can't see these things, these biological monsters. They're microscopic, right? Unlike the macroscopic
They're smaller
ones
than we are rather than bigger.
So they sneak in and they are as unknown and as unknowable as ghosts and spirits and so forth, right? So it's the frightening part of it is that what we don't understand and what we don't know. This has been true for all monsters throughout all of history.
Okay, what about Invasion of the Body Snatchers? The monster was just another
spore,
but it was a complete other human being. They didn't look weird. They didn't look scary.
That's right.
But they
had been co-opted by interstellar or non-human spores. So instead of a fungus that had evolved from our Earth, they had dropped in from somewhere in space.
From space. But you would come out of a pod.
Mm-hmm.
Some have said those are some of the most terrifying scenes
Absolutely.
ever.
Yes, because we have the closeness to humans and recognizable things, but just a little bit off, and we can imagine ourselves in that predicament.
That's where it is.
Well, that also kind of reminds me a bit of the uncanny valley and that effect with humans. If you certain animations or certain models of humans or like realistic human
Why are we
robots,
afraid of dolls?
they make
Why
us
are we afraid of clowns?
something that looks, if it's a long way from human, if it's very cartoony, we're fine with it.
That's right.
If it's completely human, fine. But if it's just a little bit off, then
That
we find that
haunts
uneasy. If
our
something
dream. We are the monsters. The monsters in space, in Monsters by Godzilla, the monsters that infect us with their fungal mycelial spores and stuff. They're just forces of nature. The thing that makes them bad is us. And this is the commentary about monsters. Once we become familiar with monsters, they're not so evil anymore. Buffy the Vampire Slayer, right? Angel. They have monsters now that are friendly, or the Twilight books. The monsters coexist with the humans. They're just part of the ecosystem. And that the monster hunters are just the people who have to keep the balance. Like the monsters go a little wild. They're a little too violent. There are a little too many of them. You have to take care of them. You have to control them. But then you have to figure out why those monsters went out of control. And in almost all cases, it's because somebody who was not one of those monsters tried to do something unwise and lost control.
So I'm reminded of Carl Sagan's, one of his several famous books, The Demon Haunted World. When I saw that title, I was like, oh my gosh.
Yes. Tremendously important.
It's the fears, the monsters embody our fears.
Yes, very much so. And also, what Carl did in that book was to make very clear the difference between a scientific and a non-scientific monster, right? Something that you could actually touch and feel and confirm and explain, as opposed to one that didn't.
On.
That's right. Do you remember in that book the parable of the dragon in my garage?
No. Tell me real quick.
The idea is that I tell you I have a dragon in my garage. And so you say, oh, let me see it. It's like, oh, no, it's invisible. It's like, well, okay, so I might be able to hear it, right? Oh, no, it's completely quiet. It's like, oh, well, it flies, right? So I can hear wind. It's like, oh, no, it flies so quietly you can't tell. And you can keep telling you that there is a thing that exists there, but I keep telling you why you can't prove that it's there. Is it actually there? In that case, this is an attempt to obfuscate or to prevent you from actually learning reality.
When children have imaginary friends, adults laugh at them. They don't laugh, but they know they'll outgrow
that. Yes,
they will outgrow this.
Right.
Yet, as adults, we have a suite of things that are just
that again reflect our fears and desires.
That's right. That things that we
them.
wish. You're exactly right, Matt. And we laugh to some extent, right? You can prey on them in your comedy shows, right? And you make people laugh at themselves, at the kinds of things that we hold in our bodies that are not physics, that are not scientific, and yet they rule our lives. And so there's nothing wrong with something that's unscientific, right? Like a ghost idea or a monster idea. It's only when you are trying to use that in a negative way or to control or to be otherwise whatever, negative toward people, that those monsters become truly monstrous.
And I find interesting that, just as a physicist, there are fewer physics monsters than biological monsters.
At the moment, that is true.
At the moment, right. And I don't know what a physics monster would even be when I think about it.
A black hole, maybe.
But it would have to have agency.
When we first thought of black holes, we thought that they were like, ooh, scary. But now it's just like, oh, it's a monster like Cookie. But there's a litany of science fiction stories, movies, books, novels, etc., that had black holes as evil, scary places for a long, long time. And then now they're
not
benign.
so much anymore.
They're
because
benign.
we fully understand them.
Because we understand them.
Yes.
Right. So,
because black holes really came in the 60s.
That's right.
And as long as you don't understand something, it's ripe for monsterizing.
That's right. And so the best way, I think, to help us all deal with the monstrous ideas or fears in our lives is just to learn more about them.
I'm a fan of science fiction, storytelling, of how inventive a next monster can be as portrayed in that storytelling. And I value anything that can bring insights to ourselves, brought to you by others, brought to you by your own introspection. And it's pretty clear that if all you do is tell stories about humans interacting with humans, it's going to miss an important dimension of how we might behave on the edges of ourselves. And a monster will take you there. And let me add a little bit of bias. If you've earned the sci in the sci-fi label of your story, and you put a little bit of biology, chemistry, physics, material science in your monster, take it wherever you want beyond that. And we're going to be watching, because in the end, the monster will teach us about ourselves.
Hey.
So, there's this latest StarTalk book that
Yes.
Lindsay Walker and I wrote.
To
Lindsay's
infinity and beyond.
Yeah, she's behind the scenes in all these recordings. We spend a large part of a chapter exploring how empty space actually is.
Yeah.
You can get a sense it's empty because there's these big, vast voids and things. All right. And so let's take a look. We have 8 planets, and they go out, 4 or 5 billion miles, but there's only 8 of them, right? So clearly that's pretty empty, right?
Yeah.
But there are these asteroids.
Right.
And most of them are collected in this flattened zone between Mars and Jupiter.
Right.
Okay. Because it's a flattened zone, we call it a belt. There are comets that come into the sun from all directions.
Right.
And if you projected where they come from, it's a spherical region around the solar system. And that we wouldn't call that a belt.
No.
Because it's a spherical region, we call that a cloud.
A cloud, right.
So
the Oort cloud.
The Oort cloud, Jan Oort, who's a Dutch astronomer. So he saw how many comets were coming in from every direction. And comets are moving fast when they're near the sun. All right. And when they go farther away from the sun, they move slower and slower and slower. So when he ran the math on this, before computers, by the way, he ran the math, he concluded there must be billions of these comets way out there in these long loop orbits that come around.
Right.
And they'll spend most of their time far away from the sun because that's when they're moving the slowest. Okay.
Right.
Pluto is the most significant member of the Kuiper Belt of comets.
Right.
So that's a belt because it's a flattened
disc
region around the sun. All right. 1801, the first asteroid is discovered. And people are excited because they think it's a planet.
Right.
They discover it orbiting in this big gap, suspiciously big gap between Mars and Jupiter. People were saying, let's just keep looking. There's got to be something there. It's a bigger gap than you think should be there given the distances between other planets. Exactly. So they found we found a planet. And then they found another one. And then they found another one. And another one. The first 4 asteroids, Ceres, Pallas, Vesta, and Juno. Ceres is the goddess of harvest, and that's the root to the word cereal. Anyhow, once we started discovering many, many, many more of these, we realized, wait a minute, they're all in the same swath of real estate. They don't sort of own their own space. And actually, they're really tiny.
Right.
They're so tiny through a telescope, they look like a star. Stars are so far away, you can't see any size for them.
But these are right here with us.
They're right here with us. So they look like stars, but they're not stars.
Right.
They're asteroids. Well, how many are there? Well, we started counting hundreds initially, then thousands, then tens of thousands, then hundreds of thousands. Right now, we're up over 1 million known asteroids with orbits and existence in our solar system.
Right.
And one of them has my name on it. It's asteroid 13123 Tyson.
13123 Tyson.
The person who discovers the asteroid has the power to name it after any person, place, or thing. So that's one of the asteroids in the asteroid belt. Okay. We know of 1 million. There's probably as many as 1 billion. Depends on how small you want to count.
What you're gonna count. Right.
All right. So now watch. That swath of real estate
Mm-hmm.
is so large, the average distance between asteroids in the asteroid belt
Okay.
is about 600,000 miles. So what's interesting is our first space, we have five, more than that. I'm old enough to remember the first 4 spaceship to go beyond Mars in the solar system to reach the outer planets. So if you want to go to the outer planets, you have to cross the asteroid belt.
Right.
Okay. We did this calculation. All right.
Right.
Early on, Pioneer 10 and 11, twin spacecraft, first to have enough energy to leave the solar system, but they're not as famous as Voyager 1 and 2.
Right.
All 4 of those spacecraft went through the asteroid belt. We don't worry about crossing the asteroid belt. We just send stuff through.
I did recently see a thing about Planet X.
Planet X. This can't be widely known because I don't hear people talking about it when they talk about Planet X.
Right.
So I'm going to give you just some backstory here. All right. William Herschel accidentally discovers the planet Uranus. We knew about Mercury, Venus, Earth, Mars, Jupiter, Saturn. There it stood.
Right.
For like millennia. He discovers Uranus. It's a beautiful paper. Nobody had ever discovered a planet because all these planets were like known to the ancients. They're all visible in the night sky to everybody.
Makes sense.
Caveman knew about the planets.
Right.
Okay. Anybody freaks out because, oh my gosh, there's more than 5 planets.
More than 5.
All right. This is late 1700s, and he's Brit. So, of course, he named it after his benefactor, who was...
Oh, the king. Yeah.
King. Which king?
George.
Of our Declaration of Independence.
That's right.
Ultimately, clearer heads would prevail, and it was renamed from George to Uranus.
Uranus.
Yeah, Uranus. So we're watching Uranus.
All right.
And we're getting a segment of its orbit because it's far out. It's not moving very fast.
Right.
These things take a long time to go around the sun. Even though we only had a small segment, we said, hey, its path is not following Newton's laws of motion and gravity. So someone suggested maybe we finally found the limit of Newton's laws in the universe. Maybe they only apply to like Earth and the moon and Earth and the sun and inner planets and the sun. That could have been. Then someone said, maybe Newton's laws do apply, but there's another planet out there we've yet to discover whose gravity we have yet to reconcile in these equations. Some French mathematicians and Leverrier, Laplace, I think, had a hand in this.
Okay.
And they communicated this prediction to an observatory in Berlin. And Gottfried Galle, Galle,
okay,
how you pronounce that?
Right.
He discovers Neptune.
That's pretty wild.
Okay, so we're now in the 1846, something like this, mid-1800s. All right. And, all right, let's follow its orbit.
Right.
We do that. It's not following Newton's laws. That started the hunt for Planet X.
Gotcha.
So people said, we've done this before. Let's predict.
Right.
Just do the math of Leverrier. Look over here.
And it should be there.
It was not there. So the hunt for Planet X was like this massive planet. It was a planet hunt like none other. Okay?
Mm-hmm.
Percival Lowell of the New England Lowells loved astronomy, was not formally trained, but he had money, built an observatory, the best one in the world. So he found a mountain in Arizona. Okay, where else are you going to put it? Right? Arizona.
There you go.
Found a mountain, built an observatory. Finest optics, finest everything. He initiated the search for Planet X.
Mm-hmm.
He wanted to know.
Yes.
Instead of choosing where to look, he starts a systematic survey in the plane of the solar system.
Okay.
A photographic survey. Now, how do you discover a planet? It has to be a dot of light in one photo, then in another photo, it is moved to a different spot. So he initiates this, brings in Clyde Tombaugh to conduct the survey. 1930 is the announcement. Planet X discovered. There's a dot in one photo, and it's moved to another place in another photo. Over the decades, we find out it's not as big and not as massive as they said it was.
A lot of ice.
A lot of ice.
A lot of reflection.
We found a moon.
Smaller than it was.
We found a moon. Its mass was like 1/5 the mass of our moon. A researcher named Miles Standish asked a question. What are the observatories that obtain the positions of Neptune, leading us to say that it's not following Newton's laws? It's multiple observatories over decades. And so he goes back and analyzes them. One of the observatories was the U.S. Naval Observatory.
Okay.
And he goes back to the observations and finds out something like the gearbox was cleaned or oiled or something. Somebody did something to the telescope before those observations were made. Anytime you do something to a scientific instrument, you have to calibrate it. He said, what would happen if I ignore these measurements and fit the orbit to the remaining measurements that are out there? When he did that, Neptune landed right on Newton's laws.
What?
Planet X evaporated overnight. Alan, welcome back to the crib here. We're here at my office at the American Museum of Natural History. And you're one of the world's, I'm not going to say one of, I'm going to say the world's expert on Pluto. You're still a vice president at the Southwest Research Institute in San Antonio, part of the space division. Very busy research institute, a lot of different scientific.
A lot of science, a lot of engineering.
Mm-hmm.
The institute was formed back in the 1940s for the public good.
Oh my gosh.
And does a lot of federal research, state and local stuff, but also research consortiums for industry. Everything from oil and gas to
Texas,
automobiles. Yeah, but electric vehicles, automated vehicles, just thousands of engineers and scientists.
Cool. So you've been there for since you left NASA.
That's right.
Okay. So you may remember I was at the launch of New Horizons mission back in 2006. And if I remember correctly, that mission to Pluto was the most powerful rocket with the lightest payload ever, just in combination, so that it could accelerate and get the hell out there before you died.
When I was a little kid, I was washing cars and babysitting and doing everything I could think of to buy bigger and bigger model rockets. You have no idea.
The kind you would launch in your backyard.
Yeah, Estes model rockets.
Estes,
right?
yeah.
Right.
Yeah.
Oh, wow. Yeah.
Oh,
Right?
yeah.
Right?
The biggest one was the Saturn V,
Right.
with like 4 D engines or something.
Right, the D-end. Then we got the New Horizons, 181-foot tall rocket, 70-foot payload bay, most powerful variant. I got to order every upgrade. I'll take the lightweight nose cone. I would like all 5 solid rocket motors.
Mm-hmm.
Wow.
Everything to make it go as fast as possible.
Right.
And then we built this little spacecraft the size of a desk, very compact. So this thing was built to launch school bus size spy satellites and big communication satellites and things like that. And we more or less took an Atlas V, amped it up with every upgrade you could think of, and then launched it basically empty. Think about this. Apollo would launch 25,000 miles an hour, 3 days to the moon.
Nice.
Tom Hanks.
Right.
Right?
Exactly.
Right? New Horizons, 9 hours.
Right. And didn't you get to the asteroid belt in 3 days or something?
Well, not that quick, but we got to the asteroid belt in record time, faster than any spacecraft, just 3 months.
Right.
And Jupiter in a year.
Okay. But this also meant by the time you got to Pluto, you were booking.
Yeah.
Right. So
how do you slow down to even take a picture
they
of
don't.
Pluto?
I mean, in the old days, we got used to flybys.
Right.
And later on, you went into orbit, but this was like the resurrection of the flyby.
Right.
Where you got to get ready for all your data in just a few seconds.
And one shot.
So anyway, it was a fond memory being there. And so it took how long to get to Pluto?
It took 9.5 years.
9.5 years.
Because it's a long way.
When is the optimum time? When is Pluto closest to us so that you can intersect it?
Right. Well, the optimum time in order to get there fast is when it's in a certain orbital position, but it's not closest. It's near closest.
Okay.
But what really matters, it's in the plane of the solar system.
Okay.
And we got there right at that exact time. So 9 years, but like the Voyagers, which went all the way out to Neptune, they had 500 people on that project. Scientists, engineers, flight controllers. By the time we did, the whole way, exactly.
Yeah.
And by the time, and we did it with 50 people.
Wow.
And so the 50 of us were doing the work.
You're doing everything.
Yeah.
Doing everything.
Yeah.
Mm-hmm.
And so we were pretty busy.
So with our friend of StarTalk, David Grinspoon, you banded together with him to write Chasing New Horizons.
Yeah.
And with this long subtitle.
Yeah.
What was that subtitle?
Inside the epic mission to explore the 9th planet.
That book was needed because Pluto was a big mystery for so many people for so long.
Well, yeah, and this mission was, so much in the public eye that really needed to be documented. And of course, David's an amazing writer.
Yeah, we all love David. So also, since then you've been in space. Was it like 4 minutes of weightlessness? About how long is
4
that?
minutes between engine cutoff and reentry. Yeah. But a hell of a ride and a tremendous experience to see the planet.
Yeah.
And I was there for a research mission.
Earth the planet.
Yeah.
Yeah. So what science were you doing on it?
Yeah, I was.
So you weren't just joyriding?
Right.
Okay.
As much as I wanted to look out the window, I was sent. I'm going to be doing a NASA mission, which is going to be determining how well the Virgin Galactic spacecraft can be used to do astronomy on these missions, like unmanned sounding rockets. And on this first mission, I did some physiological experiments using myself as the guinea pig, and also some practice for the astronomy mission, kind of get the timing of everything down.
Okay. So what else have you been up to?
Doing a lot of research, as a scientist.
Right, because your expertise is obviously not just Pluto. Your solar system objects of all kinds.
Nice.
Asteroids, comets.
Yeah, working on things all across the solar system, even the moon. I'm on Europa Clipper that's going to be launching this year to study Europa and the ocean of Europa, the plumes and the potential for biology.
The liquid undersurface.
Yeah. I'm on the Lucy mission, which is an asteroid mission. Just got launched in 2021.
Is Lucy an acronym?
No, Lucy's a pretty name. It was named after Australopithecus lucy. It's about the origin of our solar system, just like the origin of human
hominids. I see what you did there.
That makes
Oh, the Lucy mission.
What data are you gathering to tell you about the origin of this little solar system?
Well, all these missions contribute to that.
Oh.
Right? It's kind of like CSI, right? With hints and clues everywhere. The Lucy mission is a good example. The asteroids it's going after co-orbit with Jupiter. Neil won't like this, but they orbit in Jupiter's orbit, and there are tens of thousands of them that Jupiter has not cleared. Nonetheless, planet Jupiter has
these are the Trojans
Trojans leading and trailing.
Yeah.
Lucy's the first mission to go explore them. It's thought that these...
But just to be clear, so these are places in the Jupiter-Sun system where forces of gravity and centrifugal forces balance. So like Lagrangian points.
Okay.
And the objects that are there are thought to be sourced from the same region as a lot of the Kuiper Belt objects.
Okay.
So we're going there so we can compare them to the Kuiper Belt objects that New Horizons has explored.
Nice.
And we see if it's really right, if that part of the story is
correct.
correct.
Remind me, the leading ones were Trojans. Did they have a different name for the
So why do you call them
ones?
Trojans? I mean, because I'm thinking Trojan horse when I hear Trojan, but or is it...
Right.
So there's got to be some origin for why they call them Trojan.
And I'm not a historian.
But didn't they call the other ones a different name?
No, there's just a leading and a trailing cloud.
Okay.
Right, but
They're called the Lagrange points 4 and 5.
4 and 5, L4, L5. But I think only one of these packs are called Trojans, and I think the other pack...
No, they're both called Trojans.
You
they
think
are,
so?
I promise you. Yeah.
So I'm glad we're finally learning more about these objects because they're just sitting out there waiting to be...
Yeah, and they've been begging for exploration and never...
Begging.
Never.
Totally
and now
begging.
the Lucy mission is going to go see almost a dozen of them. Some of them have satellites, and we'll visit some of those.
Okay.
And that mission got launched in 2021. We just did a first practice asteroid flyby in the main belt. We're going to do another practice asteroid flyby in 2025. And then, starting in the late 20s, we'll do a whole series of...
Late 2020s,
we'll do a whole series of flybys of Trojans. And then we'll dive back in our orbit down close to the sun and come back out and go to the other Trojan cloud where we'll complete that exploration. If there's an extended mission, we'll do even more.
Wow.
And this will all end in the 2030s. So it's a long-term program of exploration.
So just to be clear, once you've established this orbit around the sun going out to Jupiter, it's minimal fuel, right? Because you've already earned this orbit.
Right.
And so now you're just sort of redirecting it a little bit.
Right. So the rocket does the initial boost, and then we do Earth gravity flybys. We've already done one.
Yeah.
We have 2 more to do to make the whole mission come. Yeah. And the principal investigator, Hal Levison, is a part of the team that dreamed up the whole geometry and orbital mechanics of how you get so many flybys into just one mission.
Right, right. This is the genius of what they got to do. Like with the Cassini mission to Saturn.
Right.
It's orbiting Saturn, but it's visiting moons every time. And all these loop orbits. Oh, let's check out this other one. You do a little adjustment. I mean, it's brilliant that we can exploit the gravitational fields of other stuff.
Yeah.
I mean, it's almost diabolical.
I'm still a little fuzzy on the difference between minor planet, dwarf planet, and planetoid. Can you
Ooh.
please explore the
You know,
differences?
I'm fuzzy too, actually.
Yeah. Some of them, like planetoid, no one uses.
Mm.
You hear it very occasionally. No scientist I know uses the term planetoid.
Wait.
I don't even hear
What do they call Thea? Wasn't that a
Thea.
planetoid?
Thea
Thea
was
that
a
made the
plan-
moon.
The term is planetary embryo. That's the term that's really used.
This sounds like a PC
Yeah,
thing. You got
that's
to add
right,
syllables
yeah.
and add another
Mm.
word.
But that is the term that's used. Is
Planetary embryo that collided with
Earth, right?
to make moon.
the Earth
I
moon
did not-
system. Embryos are basically the building planets, and there were a lot more of them originally than there are now because many of them combined through collisions to make bigger and bigger objects. Thea ended up spalling material into orbit around the Earth, and it collided that created the moon. But most of Thea ended up in the Earth.
Right.
And this was a big thing. It was the size of Mars,
Yeah.
right?
yeah.
Big hit.
So I was just trying to get my vocabulary straight here. So you would call that a planetary embryo, not a planetoid.
Because no one uses that, really.
Okay.
So now,
It's really an archaic.
Okay,
is
so-
that the same as protoplanet? The planetary
Yeah, embryo and
protoplanet,
those are
same thing?
interchangeable.
Oh, we're
Okay.
good. So protoplanet. Good.
Protoplanet.
All right. So now, for the longest while, my whole life growing up, we're about the same age. I knew of this thing called the Minor Planet Circular,
Right.
which tracked asteroids, basically.
Right.
So I always thought of asteroids collectively as minor planets.
Yeah.
Is that term still a thing now that we've added vocabulary to the system?
Sometimes it's used, and it's mostly used for the small, kind of potato-shaped, lumpy thing in the solar system, not the bigger things.
Okay.
The term dwarf planet, I'm actually very proud of this. I coined the term in 1991 in a research article in the journal Icarus, and it was meant to be
Icarus features solar system-based science.
This is the solar
distinct
system,
from
first
the Astrophysical
first
Journal.
research journal of solar system science.
Okay.
And Carl Sagan was one of the original editors of it back in the 60s, 70s when planetary science was being born as a field.
Mm-hmm.
And in 1991, I published an article that was about mathematical prediction, that there would be a large number of Pluto-like objects discovered.
Mm-hmm.
And I termed them dwarf planets in analogy to dwarf stars and dwarf galaxies
Okay.
and so forth.
Okay.
And they're meant to be
Because that word is already in
It's-
use.
It's already in use.
We already
It makes
have it.
sense.
so smaller, much smaller planets, the ones that are the size of continents. And that term's been used very widely.
Okay.
And we see dwarf planets all across the Kuiper Belt, which is part of the revolution of the Kuiper Belt that we didn't know about till the 90s, is that dwarf planets are more populous than the 4 terrestrial planets and the 4 giant planets combined. And there's one dwarf planet orbiting in the asteroid belt called Ceres,
Series.
the largest of
Which
the
was an
asteroids, which is
asteroid.
a mini planet itself.
Okay. So
Right.
Okay.
Right?
Gotcha.
Asteroid's kind of a zip code. So, it's like a Kuiper Belt object is kind of meaningless. It's just an object in the Kuiper Belt. It's like a zip code. Technically, New Horizons, the spacecraft, is a Kuiper Belt object. For the time being, it's an object in the Kuiper Belt,
Okay.
right? So that's just a zip code.
How do you go from being floating rock to planet? Because there's got to be a difference.
Well, let's back up. How do you go from potato to dwarf planet?
Oh, yeah.
The thing about potato-sized objects, so these are things that are the size of counties or mountains. And they're, most of the asteroids that you can look up in a book or that we've flown spacecraft by, they're lumpy and they have irregular shapes. And that's because that's the shape that, as they were assembled, they just came to rest in when the assembly was finished.
Mm-hmm.
And that shape is controlled by the material strength of the object.
Okay.
The thing is, as objects get bigger and bigger, more and more massive, eventually they get massive enough that their self-gravity causes them to form into a sphere. And then we call them planets.
Okay.
Once they're big enough to be a sphere, like Pluto, they're planets. The smallest of them are called the dwarf planets. And then there are larger planets that are Earth or Jupiter size. And
They're all
eventually,
spheres. And those are all spheres.
All spheres.
those are, there's a
Mhm.
continuum. They're all spherical objects.
So sphere is definitely a determining characteristic.
It's the hallmark.
It's one of them.
It's the
That's
hallmark.
one of them.
If you're on Star Trek and they show up somewhere and turn on the viewfinder,
Everything
you
is
see-
round.
you see a round, rocky something or thing with an atmosphere that's round. You go, oh, they're a planet this week.
But did we get through dwarf planet, a planetoid, planet? What?
There's no
Minor
planet.
planet.
Yeah.
See,
The
so you
minor
said there's no
planet.
minor.
Okay.
Minor
I just want to get
planet-
some more
minor
questions.
Minor planets are these little rocky guys. They used to be called, it's an 1800s, 1900s term, minor planet.
Okay.
Right?
Mm-hmm.
And that's kind of a legacy term.
All right. So before we move on to the next question, one last
In
question
fact,
for both of you.
asteroid itself is very legacy. Who was it? Not Herschel, was it? He's got his telescope, and he sees this dot of light. Like stars are just dots of light. They're so far away, they're just dots of light in your telescope. There's no, they see a dot of light except it's moving.
Right.
And it's like, so it looks like a star, but it's not a star. So asteroid. Star-like.
Star-like.
Right. So that's like the biggest misnomer there ever was.
Right.
Right. Yes, visually, but if you would care what the thing is, and we still call them asteroids, star-like from the Greek.
Does composition have anything to do with it? So let's just say that it's round, but it's an aggregate of just larger objects, but they're not really condensed. They're not really solid. They're just kind of a congregation.
We haven't seen anything like what you're describing.
Oh,
and if you look across the planets of the solar system, whether they're made of ice or rock or they're gas giants or whatever, they're all contiguous bodies, not agglomerations like you're describing.
Right.
Right? They're one big spherical thing because the gravity crushes everything into that spherical shape.
Okay.
Right? And they might have a core and a mantle and a big atmosphere above it, for example, or they might have a core and a mantle and an ocean layer like Europa,
Right.
and then a layer, an
outer layer of ice,
for example, right? But they're all the same. They're essentially spherical objects, and their shape is driven by the force of their own mass that creates self-gravity. But the same thing applies when stars collide and they can merge into a still bigger star, into a larger sphere.
Right.
Right? And it's the same physics.
I'm wondering if celestial bodies like Pluto are only able to form and exist at the extreme distance from the sun, or could they be orbiting closer, perhaps near a smaller or cooler star? And if so, do we hope finding an exoplanet that is similar, simply too small or too far away from the star to be seen from the distances involved in our observations?
The main part is could you have them close to the sun?
Right.
In fact, everything we know about the origin of the solar system indicates that Pluto formed at something like half its present distance from the sun, that the solar system is more compact originally, and Pluto and most of the other dwarf planets of the Kuiper Belt were transported outward with also the small bodies of the Kuiper Belt. But Ceres is another example. Now, Ceres is in the asteroid belt. It's a dwarf planet. Some people think it formed there.
Mm-hmm.
Others can argue that it may have come from the Kuiper Belt itself. So we don't know, but we know that dwarf planets can exist much closer to the sun.
So just for clarification's sake, the proximity of when you're talking about asteroid belt, Kuiper Belt, the sun, Pluto, and so how's it go? Where's it go?
So the sun's in the middle of the solar system, right? It's the big kahuna, right? That controls all the other orbits, right? And then we have the four rocky planets, Mercury, Venus, Earth, and Mars.
Right.
And then there's an asteroid belt just beyond the orbit of Mars.
Okay.
It stretches for something like 100 million miles outward.
Go
then
ahead.
you have Jupiter, Saturn, Uranus, Neptune.
Right.
And Neptune's orbit is 30 times as far away from the sun as the Earth's is.
Right.
Right? And probably 15-ish times as far away as the asteroid belt.
Right.
Beyond Neptune's orbit is this second belt or disk-like region called the Kuiper Belt, discovered in the 1990s, but predicted back in the 1940s and 50s. And that's where Pluto orbits and a bunch of other dwarf planets and a bunch of much smaller Kuiper Belt objects that are more like asteroids, but much more icy than the asteroids.
Wow.
And if I understand correctly, the Kuiper Belt was a negative prediction. I think Gerard Kuiper published a paper saying there should be a reservoir of objects. I don't know if he called them comets at the time, a reservoir of objects just beyond the red-blooded planets. And since we don't see any there, then he was making some inference about the early solar system. So he was using the absence of evidence as an evidence for something else. And then we find stuff there, and we name it after him.
Yeah, I think it was actually a little different. My recollection of the literature from back then is that there were really two scientists. One was named Kenneth Edgeworth, and the other was Gerard Kuiper. They were both making predictions that beyond the orbit of Neptune, that there was something like an asteroid belt that Pluto orbited in, and that it might contain other planets in it. But it was really beyond the technology of the mid-20th century.
The telescopes couldn't do it, and detectors,
And, you know, you had like Clyde Tombaugh squinting at photographic plates. They didn't have the data analysis
Clyde Tombaugh,
tools.
the discoverer of Pluto.
Yeah.
Okay.
So they had big enough telescopes, but they didn't have sensitive enough cameras, and they didn't have computers to do the painstaking data analysis.
Why didn't they name New Horizons after Tombaugh?
Why not?
Yes.
Because we like the name New Horizons.
No.
Yes, but we flew his ashes to Pluto.
What unanswered questions has New Horizons answered or you have discovered about the Kuiper Belt that researchers like yourself didn't already know or you were surprised about? Also, is Pluto's dance with Charon why it appears to be so geologically active?
A good example is that Pluto itself,
Okay.
right? We wondered for a long time if its surface would be flat or rugged. Basically, because we knew the surface is made of nitrogen ice, and nitrogen ice is structurally weak, it would make a surface that was almost entirely flat.
It's so weak that
if,
even Pluto's gravity would just flatten it out.
Yeah, exactly.
Smooth
you
it
got
out.
it. But if the nitrogen is just a frosting on top of a water ice crust, you could have mountain ranges and canyons and craters and all the rugged topography that we actually saw. So we answered that question the first day with the first pictures that came back from New Horizons of Pluto.
Wow.
And then when we went further out into the Kuiper Belt and made the first flyby of a small Kuiper Belt object, we found out how they were born, how they were formed.
This was not an accidental encounter. You're
This
targeting
was intentional.
you're targeting other Kuiper Belt
Exactly.
objects with that trajectory.
And this was a goal of the mission. And 1 billion miles beyond Pluto, we flew by this Kuiper Belt object, Erikoth. No one had ever been to a Kuiper Belt object. And from its shape, yeah, it means sky in the Powhatan Indian language.
You went to Pluto and then went another 1 billion miles?
Yeah. And now
Man.
we're almost twice as far as Pluto now
Man.
and still exploring.
Okay.
But when we got to Erikoth, from its geology and geophysics, we could determine that one of the major two theories of how planets get their start, how planetesimals, the seeds of planets, form, was wrong, and the other theory was right. And we found that essentially that these little planetesimals, the seeds of planets, form very gently through a very slow local accretion process in which they can
rather than
colliding at high speed.
collisions.
rather than collisions.
Right. And there were
Interesting.
decades in which computer models were warring, and in one fell swoop, New Horizons settled that with the data on Erikoth.
Beautiful.
It showed you pick one out of a bag and look at it up close, and you could tell one theory's right, one theory's wrong. Little material, boulders and hills
cool.
and mountains that collide with one another very gently and just stick due to self-gravity and build up a lumpy thing, not big enough to be a round thing.
Right.
Just a lumpy thing.
Right.
And tell us about the Pluto-Charon dance.
Oh, yeah, that was the other question. So the question was whether Pluto's intense geologic activity could be due to that. And it turns out not.
Due to
that dance.
the gravity.
To the gravity.
To the mutual gravity of Pluto and its big
Charon.
moon that are in a very special state called tidal equilibrium. Turns out that because of that equilibrium, all those forces that might heat Pluto or make that geology go are long gone. And
Tidal equilibrium,
Pluto's-
you mean double tidal lock.
Yeah, but that can't be the cause of Pluto's geology. It's got to do something else.
Okay.
Also, Charon, just in the traditions of the field, Pluto is Roman, god of the underworld.
Right.
And moons have traditionally been, not in all cases, but in many cases, traditionally named for Greek characters in the life of the Greek counterpart to that Roman god.
Okay.
And that way there's an homage to both
you get
cultures.
both cultures.
Right. So Pluto's counterpart in Greek is what?
What's his face? The underworld.
Hades.
Hades.
Yeah,
Thank you.
Hades. Okay. It's also the place, but it's
Right.
also the
Yes.
guy. Okay. And the ferry boat driver
And on the
to
river
take you
Styx.
across the river Styx is named Charon.
Charon.
Yes.
What's the big deal about Pluto? Does it even really matter if it's a planet or not?
It's been with us so deep in our culture that it's hard to shake any adjustments to those.
Well, that's a guess, but as a scientist, the real reason is that Pluto is the archetype. It's the heralding body of this whole new type of planet, the dwarf planets that we've discovered in the outer solar system. They're active, they have moons, they have atmospheres in some cases. Far from being a rock, it's a big spherical thing.
Right.
Right? And that's why we call it a planet. We don't know what else to call it.
So wouldn't it be cool if we just had a different vocabulary so that when I use the word, you know exactly what I was talking about? Right now, if I just say, I discovered a planet orbiting a star, so is it gaseous? Is it rocky? Is it large? Is it small? Is it? And I have to ask 20 questions just to understand what anybody's talking about.
That's the cool part of science. As a planetary scientist, you know, planet is part of the term of what our field is all about, right? And so we know what planets are. They are the things, the central objects of our field. And they are the large things that orbit stars. And they range from the smallest large, they know they're large when they become round and gravity dominates. And from the dwarf planets all the way up to the giant planets, that's a continuum of objects we all call planets. And in the planetary science research literature, there's no debate.
I don't have a problem. I'm a big fan of words. I have 6 dictionaries on my shelf over there from different eras, and I watch words come and go. I'm just saying, if you have to modify the word planet in order to know what someone is talking about, that's a clarion call for another word, a word yet to be invented that captures both of those simultaneously. And so it's a shortcoming of the lexicon. That's all I'm saying.
We have different kinds of human beings, short ones, tall ones, skinny ones, big ones, right? We have North Americans and Europeans and South Americans, and that doesn't mean we need a new term for human beings. It just means adjectives help in the English language. And there are all kinds of ways to add descriptors to planets, to stars, to galaxies. We do that all through science, right? And we got to get over these small number fears. You know, the periodic table has 100 elements in it, right? We're not afraid of a large number of those.
No.
Okay.
And doesn't Star Trek have a much more nuanced system and nomenclature for planets? There's a term, a succinct term that references, is it an oxygen-nitrogen planet? There's a gravity. There are ways of folding that into the term so that someone
You
says,
don't mind Star Trek having lots of kinds of planets. It's all good.
all in. Alan, great to have you back on.
Thanks so much, Neil.
Okay.
It's a pleasure.
All
great.
right. So this has been Star Talk.